Processes and resources. What is a process? What is a thread? How are processes and threads different? Well, a process is basically a program. What happens in the CPU is there is a program counter and there's some memory, and so what happens is the program gets loaded into memory, and then the program counter tells the CPU which part of that memory is looking at, which process or which operation is going to do next. And so that process counter continuously moves through, and then the CPU executes these commands. So each one of these programs that gets loaded into memory is a process. Within those processes, you might have different pieces of execution. And those different pieces of execution within the same process can be called threads. So if you have a process that has threads, what really happens is your process is running and your process switches between the different portions of the process to do different things. It's very common to have some larger applications have multiple threads, and even some of them are starting to have multiple processes. Games were pretty common to have multiple threads back in the day. They still have multiple threads. The idea is that maybe you want to have your audio be one thread, your GUI be a different thread, and some of your game logic be a different thread. So your audio can continuously run and not have to wait for it to make other decisions about game logic while you're playing your game. And one of the big changes with the Chrome web browser was they decided that there were too many problems with one tab would crash and take down the entire browser. So Chrome decided to break it out and have each tab be a separate process. They've changed it a bit since then, but originally that was the idea, so that if one crashed, that tab could crash and the rest of the tabs could stay live. So processes, when they crash, they can take down a lot. Threads, when they crash, well, sometimes things continue to run, sometimes they don't. It depends on how they crash, what happened. If it crashes, the whole process goes down. If it somehow gets in an infinite loop, then that portion of the thread can just loop forever, and the rest of it might stay live, keep going. So that's basically processes and threads and how they're different. So then what is a multi-core CPU? Well, there's this whole thing about Moore's law where the speed of CPUs doubles every certain number of months or years. And things kept getting faster and faster and faster, and then they ran into this problem. The problem was that when you get things small enough, it doesn't really work out so well. So they were making all these CPU pieces smaller and smaller and smaller. And when you have electricity going through a CPU, at some point the electricity jumps across and breaks things. So you have two wires right next to each other, and there's a really high charge, then they'll create some kind of a lightning bolt thing, little electricity charge between the two of them. And that can destroy stuff. So what do? Well, your electricity is basically watts. But your watts are either going to be amps or volts. So amps create heat and resistance and fun things like that. And volts, they create your arcing jump. So as you take your larger CPUs and you shrink them down, you have to worry about these volts jumping across. So what you do is you convert your volts into amps. So that's kind of nice. It means that you can go much stronger, but not have to worry about it jumping across. The problem is that then your CPU heats up more. So it's kind of a trade-off. If you have a higher number of amps, your CPU overheats. If you have a higher number of volts, the charge jump across and destroy stuff inside of your CPU. So when I first got into computers, CPUs could handle something like 200 volts, and then it got down to like 50 volts, and now it's probably even lower before they start causing problems. And they're always worried about this electrostatic discharge problem. So what does this have to do with multi-core? Well, they discovered we don't have to make smaller and smaller CPUs. At some point, they're kind of small enough. And so what we need to do is now have more CPUs on the same CPU. So they created these multi-core CPUs, dual core, then quad core, and some people even threw like 3-core CPUs, and then 6 and 8, and well, 3 and 6 are basically because they fail on a couple, but that's okay. Anyway, so the idea is you get these multi-core CPUs with multiple different CPUs on the chip. And that is what a multi-core CPU is. It's a CPU with multiple different CPU cores on the chip. So what does it mean when a CPU has hyperthreading? Well, we talked about processes, and we talked about threads, basically. The idea with hyperthreading is that your CPU tells the hardware, the rest of the hardware, it has more than one core. So if it's a single core multi or hyper-threaded CPU, then it will tell the computer it might have 2 CPUs on the chip. And so the computer sends 2 different processes, one to each one of its virtual CPUs. And then these virtual CPUs both have a little bit of memory and a little bit of other information there. And it only has one actual CPU, but the chip can then switch between them very quickly. And so it simulates 2 just switching back and forth very quickly without having to worry about the operating system keeping track of which processes are where. It just sends them both there, and they're both handled without the operating system needing to copy things out of memory and move new things into memory, what it does with other multi-process type operating system tasks. So you can have both a multi-core and a hyper-threaded CPU. So you could have something like a quad-core CPU where all of them are hyper-threaded. So instead of showing up as quad or 4, it shows up as 8 CPUs, which could be nice. It makes it so you can run things faster. But in a hyper-threading situation, you still only have one process running at a time. In a multi-core situation, you have multiple processes that can actually run simultaneously. So then that brings us down to the next thing. What is a race condition? Well, a race condition is when you have a situation where the outcome is determined by what happens and what order. So I like to think about the ATM example. Say for a moment you have an ATM machine and you want to make a $100 withdrawal from the ATM machine. If you go to the ATM machine, put your card in there and withdraw $100, you get $100 taken off your account and you get $100 that comes out of the machine. But what happens if at the exact same time you are making a withdrawal, you have a direct deposit? Let's say that you have a job, you get $200 deposited into your account. So the question is, well, does it matter what order you process these things in? So what does an ATM machine do? Well, first, it reads your account balance. It sees if you have the $100. It takes the $100, subtracts it from your account, and then it sends you the $100. Now, the direct deposit might look at your account, figure out how much you have, might add your $200 deposit into your account number and write it back to your account. So what happens if they both read at the same time? So they both find out your account balance. One subtracts $100, one adds $200, and then they both write back. Well, then it matters which one wrote back first as to what your account balance is going to be. So that is a race condition. Obviously, the ideal situation for you would probably be that you withdraw the money at the exact same time the direct deposit goes in, and the direct deposit reads, and then the ATM machine reads, and your direct deposit is the one that gets written after the ATM gets written, which means that instead of having a net of $100 more, you'd have a net of $200 more, which would be great. The bank probably not like that, though. Okay. How do I know which processes are running? Well, on a Linux machine, you can look at which processes are running. You can actually do it on other machines too. Pretty much all of them have a way to look at the processes running. And the easiest way to do that is with the ps command. It'll show you the processes that are running. You can have processes that are running in the background and processes that are running in the foreground. So a background process is one that runs and doesn't send out input to you or output to you and things like that. It's just running in the background. A foreground type process is if you have a terminal or something open and you're running a program, you will see text printed to your screen. You'll be typing things. Those are in the foreground. Background, you don't see anything, or you rarely see anything. So how do you get into background processes? Well, you can actually pull them to the foreground, and you can disconnect, output, and things like that, and these will all be taken care of. So let's take a look at a machine. So here we have a client machine, and I'm going to run the ps command. So if I type ps, I can see these are two commands that are running. The bash command, which is my shell. So my terminal opens up. It's a terminal window. Inside the terminal window, we have this program running that allows me to type in commands, and then it runs them. That is my bash shell. And the command I just typed in is ps. And so it says, well, bash is running and ps is running. If I type it again, you can see that bash is running and ps is running. Now, what you might notice is that the process ID number for bash stays the same because it's the same shell. But my ps command is different because I started one command and it printed out the output and then it ended. Then I started the next one, it printed out the output and it ended. So how do I start a background process? Well, let's try the sleep command. Sleep. If I type in sleep 5, it will wait 5 seconds, and then the command will end, and it will return back to my terminal. I can do sleep 5 ampersand and start as a background process, and it immediately gives me control of my shell again. But it's still running. If I press enter again, it says, oh, it's done, by the way. Alright, so what if I want to sleep for much longer than that? Let's say I want to sleep for 5 minutes. I can do sleep 300, and it starts in the background. And you can see there's something here. It also says that there's a process number, 5047. If I type in ps, I can see that 5047 is the sleep command, and it is running. I can also see that my bash is running and my ps is running. If I want to, I can type in jobs. Jobs says that number 1 is running. I can bring this to the foreground if I want by typing in FG. And that will take the default one, but I can also do FG1 to pull in the number. So now it's running in the foreground. If I want to put it back in the background, I can type in Control Z, which will stop it. So now it's not doing anything. And then I can do a jobs command again to see what it is, and it says, oh, it's stopped, by the way. So I can do a BG1 and start it back up again in the background. If I want to end the process, well, I can do that too. But I need to figure out what process I have. So I like PS and say, oh, okay, my sleep command is 5047. So there are a couple ways to stop the process. One is I can bring it to the foreground and press Control C to kill the process, or I can use the kill command. So if I look at the kill command, and kill, it says terminate a process, and it says I have to type the word kill, and then I give it some signal number if I want, and then there's a PID number, and all these things here. You say, well, that's great. So I can also look at other things like, well, there's a kill 2. Oh, that's interesting. Kill 2 means it's probably tied to the programming language kill. Then I got things like signal 7, which is probably more informational. So I do man 7 signal, And it says, okay, here's some information about how these signals work. And it says, okay, here are some signals. And you get some information. Oh, okay, so what does it do? Well, if I do a kill, then it's going to send one of these signals. It's going to send this sig term signal over. So the program receives the sig term and it says, oh, it's time for me to terminate. And that works. However, some programs don't like to terminate there because maybe they're crashed or something else and they won't terminate. So maybe you need to do it not from telling the program to terminate, but you want to have the operating system itself kill it, which case you'll do a sig kill, which is number 9. So let's try that. We can see, once again, my sleep command is still running. So I can do kill and 5047, and it says terminated. So I do PS, and you can see it is gone. I think, oh, I want it back. So now I'm going to start it back up again. And I do a PS command. You can see it's there running. It's going to be running for another 5 minutes. I can also do kill minus 9 or minus S9, and then the number 5246, and it says killed, which is different from what it said previously, which was terminated. It's terminated, and this one is killed. So if you're having trouble getting something to stop, use the kill command. So once again, I'm going to start this back up again. Now I'm going to do a FG to bring it to the foreground. And I will press Control-C to kill it. Now if I do a PS to see if it's still there, I can see it is not there because I killed the process. So that gives you an idea about starting things in the background and what happens there. So the next big question is, well, what happens if I close the terminal? Well, if you close the terminal, it dies. And it's gone. So that can be a problem. Especially if you log into a server, you start a process in the background, and then you log out, and suddenly your terminal is gone, and the process dies. How do you get that to work? There's a no-hup command. So if you do man no-hup, what it does is it runs a command immune to hangups with output to a non-TTY. So you type in no-hup space, the command name, and it runs it in the background without your intervention, and you don't really, well, it kind of keeps running. Kind of. You can still kill it. So let's start the sleep command again with a no-hup. No-hup. Now it says ignoring output or input and appending output to no-hup.out. Alright, so now it's running. If I close my window here, it will continue running. If I do a PS, you can still see that it is running. So I can still kill it just like I could before. And I can do a jobs, and suddenly you see it there. So if I do FG, I can bring it to the foreground, and then I can press Control-C to kill it. Or I could have killed it with the kill command. So I can still kill the process. However, it doesn't die when I close my terminal. Alright. So back to these questions. How do I start a background process? Just with the ampersand at the end of it. How do I get into a background process? You can go to FG to bring it to the foreground. You can do jobs to get an idea of which processes are running in the background. And then what happens when a process, what happens to a process when a terminal closes? Well, it dies unless you use something like no-hup to keep it alive. How do I know which processes others are running? Well, other users, who are they and what are they using? How do I know how much resources each process are using? So how much are they using? And can I end running processes? Well, we know we can end the processes because we saw the kill command. What do I do if the process refuses to die? Just give it a stronger signal. The -9 is much stronger than the -15. So let's figure out what processes are running. So I jump back into my machine here, And let's take a look at my processes. So I can do PS, and it only shows me my processes. But there's got to be other stuff running. So I do PS AUX. AUX is a bunch of special keywords, key letters. Anyway, it displays this long list of processes running. If I want to have a nice list to look at, I can do pipe through less, and I can scroll through it and see all the different process numbers, what they are, who's running them. You can see there are other users here as well. Well, mostly root, but there are users here, like the the GDM, which is your login manager thing, and caller D and postfix, which is your mail server. So all these things are running, and some of them have user accounts for it. And at the top, you can see the user running it. You can see the process ID number, the amount of CPU they're using, the amount of memory they're using. And then there's a bunch of other stats here. And the last thing over here is the command that was used to start it. Well, kind of. I mean, it's not always exactly that way. So I can go in and kill any one of these processes with the process ID number. I can also use another command, top. Top is a more active, dynamic list of processes running. So you can see which processes are running and what's going on. It tells you how much memory is being used, the total number of processes, number of running processes, sleeping processes. You can see that most of the processes are sleeping at any given time. That's what they mostly do. They sleep. And you can see how much you're using, how much CPU, how much memory, and you can sort things. We don't really know how they're being sorted right now, but you can use the greater than or less than commands or keys to shift how it's sorted. So how is it being sorted? Well, if I go all the way over, it's now being reverse sorted by process ID number. And I can go now over to user, then PR, then NI. NI is the nice level, so how aggressive it is in running and stuff like that. And VER, res, sure, has CPU. So now it's ordered by the highest CPU down to the lowest CPU. And I can switch over to memory from the highest memory down to the lowest memory. So you can do lots of different things. You can also press other keys such as K if I wanted to kill a process. So let's press K. And it says, well, there is this default process, some number, the one at the top. If I kill my gnome shell, then that will probably log me out. I don't want to kill that one. I want to kill the top command. So I do 5427. And it says, do I want to use the sig term? Yeah, let's see. Yeah, sure. So what happens? The top command now ends. So that was a quick way to end it, right? I could have just pressed Q as well. Q to quit out. That's okay. But you can see how this works, and you can see which processes are running on the system and what resources are being used by these processes. What is the proc directory? Well, the proc directory is an interface to the kernel. What does that mean? Well, it's actually a fake directory. I mean, there's a directory proc, but you have this whole entire file system that includes lots of files that don't really exist. They're not really files. They're just virtual files. And these virtual files have information in there. And some of these pieces of information are things like your CPU information. And what you do when you look at that file is you get information from the CPU, from the kernel. Actually, not CPU, from the kernel. It tells you what information it knows about the CPU. Your memory information shows you about your memory. So all these different things you can look at. So let's go take a look at the proc directory and see what we can see. So let's clear out here. If I go to the proc directory and take a look around, you can see there's a whole bunch of empty files. Well, they're like 0 size. So if I look at, let's say I take a look at version right here at the bottom. So version, 0 byte file. So I cat out version, and that's clearly not 0 bytes. But it tells me the version of the kernel running. Okay, So I cat out something like zone info. And it says, well, this is some information you might like to know. I'm not sure why I know this, but it's all there. I can cat out things like my CPU info. CPU info. And it tells me, oh, I've got a couple processors. This one right here is processor 0. It says it is genuine Intel. It tells me about the CPU family. It tells me how fast the CPU runs. And all that information. I can also do things like cat out my mem info, which tells me how much memory I have. It tells me my total memory. It tells me how much is available. And it also tells me things like how much swap is being used. It talks about dirty memory, which is basically memory that is, well, it's been loaded into memory, but it has not been written out, so there's no copy of it. And so it cannot be flushed out to swap cleanly. So you got my swap total here, my swap free. All right, so these are all these different memory information pieces. If I look back at the directory, ls again, you can see that there are a whole bunch of numbers here. And then there's a bunch of words. Numbers and words. So what are these numbers? Well, let's type in my ps command. You can see that my bash shell, once again, is 4722. So if I go into the 4722 directory and take a look around, you can see there's a bunch of stuff here. And these are different pieces of information. You can see the executable. There's a symbolic link over to my bash. And you got these, well, information about your process, your CPU things. Here, right here is the command line that was used to start my process. All kinds of pieces of information you can use, such as your environment. So different things here you can look at, you can mess with. Well, you can't mess with a whole lot of it, but some you can mess with. So this information can be useful, and this information is kind of what you get when you run the ps command. You get all of these processes here and information about them. But then there's other directories in here. Things like sys and fs and stuff like that. And they are really kind of what they sound like. Well, let's go into sys and take a look at sys. So you have in here sys. Let's go into net. Now you got IPv4, so let's go into IPv4. A bunch of things in here. All right, so what do we have? Well, one of these things is a value. So the IP forward thing right here, let's take a look at that. If I cat out IP forward, it says it has a value of 1. Well, it could be a value of 1, it could be a value of 0. So let's do echo 0 into that IP forward. Now if I cat it out again, it's 0. So you can change the values. And, well, so let's leave it as 0, but let's do ls minus L IP forward. And you can see that even though I've changed the value, it still has a value or a size of 0. So what I did is just change a kernel value somewhere. IP forward is basically the value that tells your kernel that your computer can run as a router. So why would you want your Linux machine running as a router? In fact, that was the default value. So let's put it back to 1. The default value was running as a router. Why would I do that? Well, if you ever want to set up your machine as a NAT box, you're doing your network address translation, or you want to run as a normal router, then you probably want to have that router switch flipped on. So then manually going in here and using the echo command to set it will only set it in active memory. What if you want it to be there on boot time? Well, you can do that too. So let's go down to the etc directory. There is a sysctl command, or sysctl command, and also a file. So if I cat out sysctl, sysctl.conf, I can see, oh, here we have a bunch of stuff. And if we want to figure out how do we use this, well, we could do, look at the man page, man sysctl.conf, and it says, okay, well, all you need to do is figure out what you want and put them in here and tell it what you're doing. Okay, well, that's kind of confusing. So what are we doing? It also says you have other files you can look at. There's the etc sysctl.d directory, which has a bunch of conf files. So let's take a look at that one. Sysctl.d directory, and you can see there is a 99 sysctl.conf file. Okay, so it says, all right, we just want to load this one first, or not first, but after everything else, because they're in order. And all it says is, well, the sysctl.conf file we just looked at. So if you wanted to have something start up on boot time, you could use the sysctl.conf file to make it happen. So how does that work? Well, the IP forward command had this long path. So if I do ls minus l, u is proc sys net IPv4 before IP forward. That was the file. Now, everything from sys, after sys, this net IPv4 IP forward is all you need to know about. So I can go into my sysctl.conf file, and I just need that part right there. Net IPv4 IP forward. So go down here and do a net dot IPv4 dot IP forward equals 1. And that right there will set it up so that when it boots up, it will set the IP forward to 1. Well, it's already being set to 1. So I could change it to 0 if I wanted, but that's how you do it. You set values in there. You can also use the sysctl command. Sysctl, how does that work? Well, it says you type in your options and your variables and values and stuff like that. You can do a -p to read from a file. So I just do sysctl -p, and it sets my net IPv4 IP forward to 1 because it's reading it from the file, the default file. I can also have other files I read from as well. But that's how you set those. Alright, so what other variables are stored in the kernel proc directory? Well, we saw the IP forward. Can I change things? Well, we know the answer to that. You can use the echo, and you can also use the sysctl command. And that brings us to the last question. What is the sysctl command used for? It's for changing those things. Alright, file systems. How do I know how much hard drive space is being used? That could be important, right? How do I know how much space is used in a directory tree? We can do that too. We'll look at that in a moment. And then what happens when the machine runs out of drive space? I'll tell you, it's very bad things happen. If you think about it, we have a journaling file system. So, in theory, what would happen if you absolutely ran out of space? In order to write something to the hard drive, usually you have to write to the journal first, say I'm going to make changes to the hard drive, and then you make those changes and then you remove your entry from the journal. Well, what happens if the journal takes up extra space? Then you cannot write to the hard drive. In fact, there are some file systems that are written so poorly that once the hard drive is completely full, if you try to delete a file, it has to write to the journal that's going to delete the file, which it can't do, so it can't delete the file. So the only way to get it clean is to completely reformat the file system. That's a very poor design. So that can be really bad. Don't ever run out of hard drive space. Linux is fortunately written by people who are much more intelligent, and they leave a little bit of buffer space and things like that so that you can still do stuff even if you run out of space. They kind of run out without actually running out. So how do I get more space? Well, you can delete things. You can add more hard drives. And if you have something like an LVM in there, you can add more hard drives and expand your current drive size, and then use your file system tools to expand your file system in your drive space. So let's go look at the file system, see how much space is being used, and how we can look at directory trees. So let's jump right in, clear that. If I type in df, it tells me information about my space being used. Now these 1K blocks are great. We love seeing 1K blocks, but what does that really mean? Well, let's do a df minus h into human readable form. It tells me, okay, this is how much space you have. And it rounds these things a little bit, so they're not quite exactly accurate, but you know, it's accurate. All right, you can see which devices I have, and then how much space is available on each device. You can see that there really are only two devices that have real space. You have your first one right here, your CentOS root, which is your main file system. And I also have this boot directory. The rest of these are all kind of virtual-ish things. They're not really real. They're kind of more memory things that are kind of fake-ish. So they don't really count. But those two are real hard drive space. All right, so I know how much space is there. I know how much is left. But what about directories? How much is being used by my home users? If I look at my home directory, I can see there's a Joseph person there. So if I go down, take a look, I can go into my home directory. I can go into Joseph. I can look around and see how much space is he using. Well, it looks like he's not using very much. How do I find out how much it is? We can sit there and add everything up. Or you can have the du command do it. So du, and let's do the home directory. It says, oh, 12 is being used. What's 12? Well, let's once again use the minus h, which happens to be the human readable form. And it says, oh, it's 12K. Like, oh, okay, thank you. What about the user directory? If I do a du minus h on the USR directory, well, that's much larger because it has to go through and parse through all of these directories and figure out how much space is being used in everyone and add it all up, and it comes up with a total and says, oh, the entire USR directory is 3.5 gigabytes, more or less. I could do that in less human readable form if I wanted to get more exact numbers, and it'll say, oh, this is the number of blocks being used. These are the 1K blocks. And that's how you can figure out how much space is being used on your system. Anyway, these are, that's how you can figure out the space. That's how you can figure out what's in a tree. And once again, don't run out of hard drive space. Bad things happen. And that is the end of this video. Kernels and hardware. When you're running a Linux system, you might have questions about a kernel. Well, first of all, what is a kernel? Well, the kernel is the main program that runs your operating system. It's the main thing. So Linux is the kernel. So which kernel version am I running? Well, there's lots of different kernels. Which am I running? And where is the kernel file stored? Where is the source code for the kernel? And what options were used when building the kernel? So let's take a look at these questions and see if we can figure them out. So here we have a system. I'm running my Linux system, and I want to know which kernel I'm running. Well, if you look in your etc directory, there's a bunch of files in there. So if we cat out our etc, there's a Red Hat release file. And that tells me which version of CentOS I'm running. But it doesn't tell me which kernel I'm using. So that's kind of tough. So you start saying, well, where else could it be stored? It actually turns out there's an easy way to do it. We just type in the uname command, uname -r. And that tells me my kernel. So my kernel is 3.10.0 957.12.1.el7.x86_64. So these EL7 maps up to this CentOS release thing, which is 7. Same 7 right there. Now the 7.6, well, that is kind of tied to the Red Hat release, and this 18.10 basically tells you which CentOS release this is. All right. So we've got that. How is the kernel built? Well, most things on a Linux system are built with the GCC compiler. But do we know if it was built with that? Well, we can actually take a look at the kernel, and the kernel can tell you something as well. So cat proc version, and we see once again that same exact number. So this number right here, the kernel number, is showing up right here. So that's the kernel. You can see where it was built and the GCC version that was used to build it. Alright, so that's good information. So where is the kernel file? I mean, it's built, it's loaded in memory, I get that. Where is it at? Well, fortunately, you can find it in the boot directory. And some systems have boot mounted by default, some don't. You can always cat out the etc fs tab file and see what it says about your boot directory. It's got my device here, so UUID, and then this boot, and it says xfs defaults. So it's not being not booted. Sometimes it doesn't actually load for some older Linux versions because they don't plan on changing the kernel often, and so they just don't load it. And it also protects it a little bit. But it is mounted, and it should be there. So I go over to the boot directory and take a look. There are a bunch of files here. And if I go back to my uname command, once again, I can see this is the number I'm looking for. So if I do ls minus, let's do L, and then pipe that through a grep, and we want to do a backtick, uname minus R. So what we're going to do is we're going to look at all of the files, and we're going to filter out just the ones that happen to have that string in them. Grep, uname minus R, minus R in there. All right. So you can see there's a bunch of stuff here. Okay, what is it? Well, this first one on the top is your config. That is the configuration options that were used when creating this kernel. So, as you might expect, you less out that config with 12, and you'll see a bunch of options, tons of options with yeses and modules and not set and things like that. And you go through, you say, okay, so that's how the kernel was built. All of these options are set. And there's lots of options. You just kind of keep scrolling through them. Lots of options to set. All right. Then you have this RAM disk thing. RAM, init RAM FS. Well, it's the initial RAM disk file system thing, and that's kind of important. What does it have? Well, when your kernel gets loaded in memory, the way it happens is you have your, your BIOS loads the first part of your hard drive. And the first part of your hard drive loads your bootloader. And your bootloader looks at your configuration files, figures out what to load, and then it loads your kernel. And when it loads your kernel, there's always that risk. There's a slight risk that your kernel will load up and it will not have the drivers in order to read the file system. So that could be because you have some kind of a RAID set up. Hardware RAID, you need to have the hardware RAID drivers in there, otherwise you can't read the RAID, and if you can't read the RAID, you can't get anything from the hard drive. Could be all kinds of problems. But the BIOS, when it's reading, it reads things differently than the kernel reads them. So it has the ability to read things that the kernel cannot read. So that could be a little interesting. So it's always possible to get in a situation where your kernel is loaded, but your kernel cannot read the hardware because it needs some kind of drivers. So where do you put those drivers? Well, you can put those drivers in the initial RAM disk. And so you put drivers in there, these little kernel modules, and they get loaded, and then it can suddenly read the rest of the system. So that can be important. Let's get down to the bottom. We've got this VM linez thing. So the Z is for compression. It's basically a compressed file. It's really a larger file. And that is your kernel. That's your kernel, built out, compressed, waiting to be loaded into memory. So that's what happens. That gets loaded. But then where is the source code? Well, source code for the kernel is usually stored in the src directory. So let's take a look over here. We've got this directory called kernels. So let's go in here and take a look at our kernels. Kernels, take a look, and it's empty. Why is it empty? Well, if you think about it, most people don't need their source code for their kernel, right? You just want the kernel to run. You don't need the plans. You just want it there. So some versions of Linux ship without the kernel. Well, that can be a bit of a problem, because what happens if you need the kernel? Well, that's okay. We can get pieces of the kernel. So when do you need the kernel? If you are changing some of your libraries, and your libraries need to be able to access the kernel, so you need to make system calls to grab stuff from the kernel, you might need to have your kernel headers. And the kernel headers can be loaded with a special package. So let's look. If I do a yum install kernel devel, it will install the kernel headers. So I do yes. Now, contrary to common belief, if you install this kernel devel, it doesn't give you everything you need to develop the kernel. No, not quite. Not that at all. In fact, all you're really getting is the kernel headers. Quite a small little piece of information. You need more in order to actually build the kernel. But we can go in there and take a look. So now we suddenly see there is a directory here. So I go to that directory, and I can see all kinds of files here. And one of the files is that config thing. So cat.my.config, and I can see this looks like, well, a bunch of the same thing that we had in that boot directory. If I do a diff to compare my .config in this directory, config, to the one in boot.config, right here, you'll find those two files are exactly the same. So there's no differences. So that's great. That's kind of nice. But what if I don't want this kernel? What if I want to get a new kernel? Well, you can download it. Or what if I want to actually build a kernel? Well, you can do that too. In fact, you can look at your options even. There is a menu config thing. You can do a make menu config and look at your options, but it doesn't quite work without some development tools and a little bit more. So let's do a yum group install. And we're going to get our development tools. That's the entire development tools package set, which includes your GCC compiler and all kinds of other libraries. So this will get you most of what you need in order to be able to see what the kernel needs in order to be developed and some of them. So after a couple of seconds, it's all downloaded and you're ready to go. And I want to do a yum install ncurses. Ncurses allows me to have menus. So I can do up, down, navigation through menus with the keypad. All right, so I do a make menu config. So I want to make sure I'm in this directory, which I'm in. You can see I'm in the correct directory. You can see there is this make file here, which allows me to run the make command. So I do a make menu config, and that will do this right here, print a few things, and suddenly it'll pop into a nice GUI right here. And I can go look at the options that were set at the time that this kernel was built. You can go into individual things, say, okay, do I have the second extended file system that's ext2? Do I have it? No, I don't have it. Do I have ext3? No, I don't really have it. But I do have ext4. That's great. And ext4 can read ext2 and ext3. We just want to make sure we use that. And so you can say, well, what if I want something like ReaderFS or JFS or XFS? I can put those in there. I can even build it into the kernel if I want to not use modules. But you probably want to just use it as a module because maybe you're not using XFS. But if you know you are, maybe you build it in. All right. So exit out. And if you make changes, you can save those changes, and that's good for building your kernel. Usually what you do to make your kernel is you use the make command and you do a, well, make all. But that doesn't really work here because we don't have the source code. So where do we get the source code? Well, the source code actually can be found in other places such as right here in kernel.org. You can see kernel.org. You can see the Linux kernel archives. Has a bunch of files here. You just download one of these tarballs and decompress it in the USR SRC kernels directory. And then from in there, you can just go inside of it and build it. You make sure you have your development tools, make sure you have ncurses, make sure if anything else is missing, and yeah, then you're good to go. All right. But that doesn't really get it all taken care of. So let's go back and see what drivers do we actually need, right? Because you think about it, you've got this thing. We know where the kernel, what version you're running. You know where it's stored. You know the source code's not there, but you can get the development headers if you want, which can be used for building other stuff. And you know what options were built or used when building it. So how do I know what hardware I need to use? So you need to know what hardware you have on your system. And you can figure out which USB devices you have. You can see which PCI devices you have. You can see which drivers were used or are being used. And you can see specific versions of all kinds of stuff. And this information is going to be useful. So let's take a look at it. So if I do ls USB, it says, these are the devices that are connected to me. Okay. Well, these are the kinds of things I got, which is kind of nice. Doesn't really tell me much because there's nothing really there. I can also do ls PCI, and that says these are the PCI devices that I have on my system. Well, what if that's not enough information? What if you need to know more information than just that? Because I can see, okay, I've got a VGA compatible controller thing here. That's nice. So I know that's what I need for my graphics card. And I can also use my Ethernet controller right here. But I don't know what drivers I'm using. So you can do a LSPCI -V for verbose. And that says, oh, here's some information. And you can see, for example, my video card right here. Got some information about it. That's nice. Drop down to my Ethernet controller right here. And it even tells me things like, this is the driver. This is the kernel module that's being used. The E1000 is being used. Some of them tell me the drivers, such as the sound cards and PCI things. All these things are showing up and giving information. But what if that's not enough information? What if I want more? I just add another V. Suddenly we have more. What if that's not enough? I want more. I just add another V. Okay, so it doesn't give me that much more. So really 2 V's is about as much as you get, but you can use 3. So add a couple of V's and you're good. You can see what hardware you have with this PCI thing. So why is that important? Well, you need to know which drivers you're using if you want to guarantee you have them when you do your installation or building of a new kernel. It can be kind of important. You want to make sure that they're either built or make sure that they are built into the kernel so that you don't need to build the modules. Kernel modules. So what are kernel modules? Well, kernel modules are your drivers. They're the little pieces of kernel code that gets loaded in and used. So you might say, well, why would I build kernel modules for hardware I never need or don't use? Well, I don't know. Why would you? Well, you might use it. But if you know you will never use something, you don't need that module. It's not necessary. So then, why were the kernel modules built outside of the kernel instead of in the kernel? Well, the reason they're built outside of it is because you don't necessarily need everything. And there are even problems where multiple different kernel modules can conflict with each other. And you can't have two of the similar modules because maybe one will work and the other one won't. There might be two different modules built for the same hardware, and you only want one of them. Maybe one's open source and one's a proprietary closed source. And that could be, well, a good reason to have them outside the kernel because you can only have one in the kernel. And if it's in the kernel, it's guaranteed to be in the memory. And what if you don't ever use XFS or ext2 or 3? If you don't use ext2 or 3, why would you want that kernel module built into your kernel? Just don't build it. So which kernel modules are loaded? Well, you can use the ls-mod command to see which ones are being loaded and things like that. So let's go take a look at that right now. To clear this up, I do ls-mod, and suddenly it shoots us a big list. So we knew we were using the E1000 driver for our network card, and we can see right there it's being used. It's the E1000 is loaded up, and it's in there. But you can see lots of other drivers in there as well. So which drivers do we have? Well, you can do mod probe, and that kind of tells me something. It says, well, here's some things you can do. And it's just saying, well, what do I have? And you've got this -a option. So let's figure out what that does. So do mod probe -a. And nothing there. We want to, usually you can use mod probe to load drivers, and sometimes you can use it to list the drivers as well. Let's clear this up. So let's approach this a different way. So mod probe apparently doesn't have the option anymore to look at all the modules, but we can still load modules. And let's take a look at the directories where they are stored. So if I look at the lib directory, ls -lib, there's a lib modules. All right. So that's interesting. There's a lib modules. And then we want to get our kernel, which is 3, right there with the 12. And we can see this stuff right here. Well, that's a lot of modules, right? Maybe. So we use the find command, find, and we can list out a bunch of things in here. Well, we know that we want to look for let's find their network driver. So we know it's E1000, so we do grep E1000, and we can see suddenly this is where you can find the drivers for the E1000. There's the E1000 and there's the E1000 E, whatever that is. But you can see the directory where it's stored, and you can also see the actual module stored there. And most of them end in a KO, but these ones are apparently compressed, so they have an XZ at the end. And so these all get loaded at boot time. And well, when it gets loaded. And sometimes they get loaded at other times. So once again, if you look at ls mod, you can see the list of modules. If I wanted to remove a module, I can do that as well with an rm mod or ins mod for insert mod. And mod probe, once again, can add or remove modules. So those are a couple things with kernel modules. So we can see, first of all, which kernel modules are loaded with the ls-mod command. We can see which kernel modules there are by just doing a look at the lib modules directory. And then how do I load kernel modules? You can do mod probe to load them, or insmod. So why would I want to build my own kernel? Well, sometimes you want to build a kernel for a specific purpose. Maybe you don't want to have any extra modules built in. Maybe you want to just build a kernel that specifically meets a set of hardware and you're done. If you do an embedded system, you want to make sure your hardware meets exactly or matches exactly what the kernel has. Are there any performance advantages to building a kernel? Yes, there are. You can build a kernel specifically for your hardware and then you can optimize everything. Is that a lot of work? Yes, it's a lot of work. How do I build a kernel? Well, first you need to get the source code. And we saw where to get that because you get it from kernel.org. You download that. You put it into your user src kernels directory. Decompress the file. You go into that file and you then can make sure you have your libraries installed, and you can do a make menu config and set your settings. If you want to copy over a config, you can copy over a config from a previous or different version of the kernel that you know works, and then change the settings up a bit. Then you do a make all, and it will build it. Why do I need a compiler? Well, you need a compiler because you need something to convert your source code into machine code. How long does it take to build a kernel and the modules? Well, that's an interesting question. It depends on what your CPU is. If your CPU is a nice, slow virtual machine CPU, it could take you, I don't know, 2 to 3 hours to build your kernel. If you were building on much harder, faster, multi-core CPUs, you can do it much faster. You can do it in 10 to 20 minutes. So why does it take so long? Well, there are a lot of files. There's millions of lines of code in that kernel. So you are looking at a lot of stuff, parsing a lot of stuff. And it depends on how many options you build. The more options you put in there, the longer it takes. Once a kernel has been built, how do I change which kernel I'm using? Well, remember the bootloader loads the kernel, right? So all you need to do is tell the bootloader how to load your kernel. Alright, that sounds pretty easy. So how do I change the default kernel the system is using? Well, with the bootloader. And let's go take a look at that. So clear this out, the bootloader. So let's drop back to that boot directory again. In here, there is a grub and a grub2. So let's take a look at the two directories. So if I do ls-l grub, I can see a splash.xpm.gz. That is the splash screen you see when you boot up your system if you're using grub. So it's being loaded. Great. That's not where you make changes. If you go into grub2, this is also not where you make your changes, but you can see what changes have been made. There's a grub.cfg file here. So let's take a look at that one. Grub.cfg. And it's got all this information here. But what's useful is it tells you basically where the files come from. So it's a collection of files from the etc grub.d directory. So it goes through and it reads in these files. So it takes this first one, 00_header, and then it puts the header in there. And then you can see it's adding each piece one at a time. All right. Well, if you go down here, you see there's this 10 Linux, and you can see there's an option here, menu entry. Menu entry. So whatever here is in this menu entry quote is what you will see when you're booting up. That will be the option you can choose to boot. And then it tells you things like which modules have to get loaded. And it then has this line right here, Linux 16, where it tells you this is where you load the Linux kernel. Then right after you load the Linux kernel, you load the initial RAM disk. So it loads that image right there. So those two get loaded, and then you're good to go. So How do I know what it's using? Well, it says a couple of things that are interesting here. There's a timeout that says you got 5 seconds to actually choose which kernel you want to load. And yeah, you can also figure out which kernel is being loaded because you got this default value, things like that. Okay, so what do? We just need to go in there and change what the default is, right? Or you can add another line in there. So you go to the etc grub.d directory, and in here you can see all these files that are then thrown together to generate your kernel. If you look at the README file, let's README, you can see information about these. Well, okay, so these are how it does it. So you've got these 00 things for reserved for the header. You got this 10 stuff for your native boot entries. And then you got this 20 stuff for your third-party app stuff so that they can all jump together and build it up. And it builds this when you run a script or program to do that. So now let's look at how we can actually generate this. You can generate these things, and you gotta be sort of careful when you get to some of this stuff, because if you mess things up too badly, it can be bad. But there is a grub2 command. You can see there's a bunch of commands here, but grub2 make config, and that one will generate your configuration file. So you'd want to do -o and tell it your file. So you do like a boot grub2, and if I want to do a grub.cfg file, I can do that. Let's just do a new so I can compare it. So I run that command right here. It grabs all the stuff. That's good. So if I go over to my etc, actually not my boot grub2 directory, I can see I've got a grub.cfg and a grub.cfg.new. If I do a diff on the two of them, grub.cfg and grub.cfg.new, I can see there are a bunch of differences. What are they? Well, things like, this one, different versions of the kernel, so it's changed the menu options. It looks like I basically just got a new kernel, and I haven't installed it yet. But that's about it. Right there is just slightly newer kernel. Alright. And also it changed the default things like that. So you can mess with your grub configuration there. You can also do things like set a password. There's a grub2 make password thing, and you can run that and type in some password like aloha123, aloha123, and it will say your password. You just need to copy that piece and install it into your grub configuration files if you wanted to add something. But yeah, you can mess with your bootloader and change it, and that's how you can work on installing your new kernel and making things work. Mess with grub. So your etc grub.d directory, and then you can just build your grub configuration file at boot time. Anyway, that gives you an idea of what grub is. So is it important to be able to change your kernel? Yeah, sometimes, but it's done automatically whenever you install new kernels. It automatically rebuilds everything for you. Anyway, that is it for your kernels and hardware. System logs and queues. So what are system logs? Well, system logs are basically files, some kind of file that stores information about events that happen. So when something happens on your system, it's usually sent to one of the many log files in the var log directory. And then those files record the events and allows you to look back and see what happened in order to lead up to certain situations you're in, or to figure out what's happening in your system. So what kind of information is stored in the system logs? You have your regular messages. Whenever you start and stop services, that's starting there. You have logs that indicate whenever you boot up your system, what options and things happen there. You have logs that indicate things like mail coming in, going out. You have logs for your web services. You have logs for logging in, logging out. SE Linux has a set of logs. All of these things are in the logs, in the log directory. So why do logs take up so much space? Well, logs are written anytime some major event happens. And there can be lots of different events that happen, and all these events have a line entry or more in the log files. If someone tries attacking you, you can actually fill up the entire partition that those logs are stored in because you start generating too much data, and it's, well, bad. And if the logs completely fill up the system, well, it depends on where the logs are. So some people will put their logs, their var log directory or their var directory, in a separate partition so that if it does fill up all the way, the system can continue to function. However, if it's not in a separate directory, then whatever directory or whatever partition they're in could completely fill up. And if that's your main boot, maybe not boot, but your main root of your system, that means your system might become difficult to use for anything. So you got to watch out for that. So who reads all these logs? Well, lots of people can read the logs. Well, some of them anyway. But there are some files that can be read only by people who have special rights. So the root user or administrators who have the ability to become root. And those logs usually have more sensitive data. The less sensitive data can be visible to all users. So why can't normal users read all the logs? Well, imagine if someone were to try logging in, and so you saw a login attempt with some username, and you noticed that username looked very much like a password. And then right afterwards, after they failed to log in, a user logged in. And they logged in with a correct password apparently, but you see their name. So then you might be able to take that password and that name and put them together and figure out what the user and password pair is. That might not be something you want normal users to be able to see. Also, other things, if you try doing something bad on the system, maybe you'll generate a log and you don't want that log entry to, well, everyone to know what log entries were generated when people are doing bad things, because then they can figure out what they can get away with without having logs generated. So it can be helpful. So let's go take a look at the log files and see what we see. So if I jump over here to the var log directory, I can see a lot of files. And there are, well, lots of them. Some of them are big, some of them are small. But let's just go through some of the main ones. So we can see that there is a dmessage file at the top. So if I cat out dmessage, D-M-E-S-G, you can see this is information about how the system started. You can see what started, what order, and that can be useful for a few things. Also, you can see there is this last log. Last log is, well, let's take a look at what we can see here. Last log. It looks hard to read. So you can actually type in last, and then it will tell you who's been logging in and when they've been logging in and information like that. It is a binary file, so we can look at it using that tool. You have messages. So let's cat out messages. Messages is where your default log files are for everything. You can see lots of things running through. You can scan through it and figure out what's happening if people are having login failures, all that information. Also, you have the secure log. That shows your logins attempts as well. Cat secure. You can see all of your PAM Unix things, which is basically your login attempts. All right. Then, after you see all that, you know, there's a few other logs in there, but there are some directories as well. So let's go look at these directories. So there is one for audit. So if you go into audit, this is where your SE Linux audit logs are. You cut out your audit file, and you can see all of these SE Linux violations or passes. And you can see what succeeded, what failed. If something failed, it will tell you in here what failed. And this can be very useful for troubleshooting problems. If you're doing something on the web and the web's not working properly, you can go look at your web logs, assuming you have Apache installed, and you can look at your web logs and you can see those, but maybe it wasn't a violation there. Maybe it was an SE Linux violation. And then you can go in here and look and see, is there something showing up? All right, if I install Apache, for example, I will see an HTTPD directory show up. So let's do a yum install HTTPD, just so we can see the directory. And now I can see that there is an HTTP directory that just showed up. And I can go into this directory and take a look at that. Nothing here, but then you'll see an access log and an error log whenever there are problems with your web pages. All right, so those are your log files. So what is the var log messages file for? Well, it's your standard default location for your log messages. For any log messages, if you don't have something specific, such as SE Linux has its own audit directory, and HTTPD or Apache has its own HTTPD directory. If it isn't one of those type of services, or it doesn't have something special, it might just write it to the messages log directory, messages file. Can you read it in real time? Yes, you can. It's not very exciting if there's something happening, but you can read it using the tail command. So let's take a look at how that works. If I wanted to look at it in real time, I can do a tail -F messages. And you can see, I press enter a few times, that's what happened. There's nothing going on. So if I were to pull up another terminal over here, and let's say, oops, I pulled up a terminal, that didn't do anything. But if I were to install something, so yum install, let's do nmaps, it is there. It's probably already here. Oh, I guess not. You can see that suddenly it says, oh, installed nmap. And you can see that showing up right there in the logs. If I do a yum update, which could probably be a really bad idea from the GUI, but it's nothing replacing GUI. If I do that, you can see suddenly it's showing up a whole bunch of stuff being updated. And you can see those in real time if you're looking at the messages file with the -F switch in the tail command. So tail -F, the file, and you can see changes happening to that file. All right, you press Control-C to get out of that. Can the logs be changed? Yes, they can. I can go in there and edit the logs if I wanted to. I could delete things out of it. So if I were some kind of a hacker and I wanted to mess up your system, what I'd probably do is either edit your logs or just delete your logs altogether. So I've had hackers hack into my systems before and delete the logs. And if you notice your log directory is all empty, well, that's usually an indication that something bad happened and some got in your system. The var log secure. So var log secure, once again, I mentioned that one indicates who is logging in your system and if they are failing to log in. So what information is stored in that directory? Well, it's got attempted logins. So let's go ahead and fail a couple of logins so we can see what that looks like. So I could do a tail -F secure. So you can see where it starts. I'll pull up another terminal right here. And now I'm going to fail a few logins. So I do SSH root localhost. Yeah, sure. Password. Nope. Nope. And you can see that it is failing to log in. And then you can look at this and say, well, what happened? Well, You can see failed password for root, and it says where I logged in from, so it's actually saying, well, I should use IPv6, logged in locally. Okay, from localhost. That's fine. But if you see it from a different IP address, what tends to happen is there are a lot of script kiddies out on the internet, and they are using these lists of passwords, and they'll just sit there and guess your passwords. And, well, try to guess your password. And they grab all the common passwords, and if one of them goes through, then you'll get hacked into and it'll be over. So don't pick a common bad password, or bad things can happen. So don't do that. All right. Can I use the information to identify hackers? Yeah, you can. You can see that clearly I came in from ::1, which was my IPv6 localhost. Can the information identify users who are doing things, or can I identify users who are doing things they should not do? Yeah, sometimes. It depends on what you mean by identify users also. Sometimes they are trying to switch over to root when they're not supposed to, and that could show up. Sometimes, other things can happen. But what it really tells you is what user is trying to do it, or what IP address is trying to do it. It doesn't tell you who the person was or where they came from. Can I use the information to detect system compromise? Well, sometimes. Sometimes you can't. Sometimes all you can see is that they were attacking your system and trying to get in. But that doesn't mean they got in there. Can I use the information to identify users who forgot their passwords? Maybe. You can see who's failing login. Does that mean they forgot their password? No. Does it mean that they're a hacker? No. It could be either one. It could be other things as well. It could be their cat jumping on the keyboard. We don't know. All you know is that someone is failing login. And that's all you see there. What does it mean to rotate logs? There is a program you can install called log rotate. And what that does is it will take all of your log files, or many of them, and every week or whatever set period of time you want, it will rotate the logs. And what that means is it will take the existing log file and move it to a new file with a number extension, and then it will create a new file. And what happens by doing that is you can then decide how long you want to keep logs for, and if you want to just let logs disappear after a month. And then your system might not run out of space and might not crash. Can the log searching process be automated? Because I can look at those logs right there, and there is a tool called LogWatch, which you can install, which will go through once a day, a little cron daily thing, scan through it and figure out if there's anything that looks suspicious, and then send you an email to let you know what things can or are bad. Can logs be stored on a different machine? Yes, they can. So your logging utility is usually your syslog program, and there are different syslog programs, but your syslog program can be configured to send your logs to a different machine, which can be useful if you want to save your logs. You can also configure your Linux machine to receive logs from other systems. So you have your Cisco routers and switches all send their logs to this machine, and you get them all consolidated in one safe location. Then if the router switches get hacked and the logs get messed up, well, they're already on this machine, they're gone. So you've got a copy and they're safe. Queues. What is a queue? Well, a queue is a line, right? It's a British word for line, kind of. You queue up, and, well, that's what a queue is. So what is it on the computer? Well, on the computer is basically a line. You have these things that are getting ready to do something. So you get them ready. You can have your mail queues and things of that. So then what's a spool? Well, a spool is when you think of like a spool of thread or something, things are wrapped around it. Basically, it's kind of feeding things through something. You're spooling it through. So spooling your print jobs from your application to your print daemon, which then spools it off to your print server or to your printer, and it eventually gets printed. That's spooling, passing things through. And queues and spools can kind of be thought of as similar things. They're a little different, but they are used for the same kind of purposes. So what queues are used on a Linux system? Well, let's take a look. So I clear my screen there, jump down to the var, and there is a var spool directory. In this var spool directory, you can see a couple different things. We can see var spool postfix, var spool mail, var spool cups, var spool LPD, var spool cron, like lots of different things. So postfix is my mail server. My mail directory is my, well, incoming mail. LPD and cups are both for print services, so that's kind of nice. Cron and at and anacron are all for timed task management. So yeah, you kind of get an idea there. Let's take a look at the mail directory. Oops, cd mail. You can see there is a Joseph and an RPC, but Joseph is empty. If I were to have a mail client installed, I can do mail, should mail Joseph, and I can have a subject say something, and say, hey there, and have a period by itself, and close it. And then if I take a look around, suddenly I see Joseph got mail. So I just sent him mail, and it went into this mail spool thing. So if I cat out my Joseph file, I can see all of the mail that got sent to him. So you can see who it's from, information about where it's to, subject, the from line, and then the contents of the email all showing up right there in this mail thing. If I send another email, it will show up in the exact same file, just added to the end. If Joseph logs in, he can then read his mail and he'll pull it out of this file and into his home directory. So that's that directory. All right, what about cups? You can see just temporary stuff here. LPD, it's basically the same thing. They're just printing services. If I go into postfix, though, you'll see something more exciting. It's got a lot of different directories. You've got the incoming, you've got the outgoing stuff, the bounce directory. Well, if you think about it, a mail server is a lot more complex than you might think. I guess if you think about it, yeah. So what happens? Well, you drop your mail into your program. This mail program, it puts things in here. It looks at them. It tries to send the mail. It receives mail. If it can send mail, it sends it. If it can't send it, it might have to sit there and defer it or bounce it or something else. It depends on what's going on. And so this keeps track of every single piece of mail and what state it is going through this mail system. So that can be useful. So let's jump back over here. So where is incoming mail stored? Well, we just looked. It's in the var spool, and then you have to decide which one you're looking at. What do you mean incoming? Is it incoming that's already arrived or incoming that's incoming? If it's incoming, it'd be in the postfix directory if it's using postfix. And outgoing would be in postfix as well. So var spool postfix. But once it has gone through postfix and been processed, it'll get put into var spool mail. Why do I care about mail? Well, lots of different tasks and things on the system will use mail as a way to communicate with the users. So whenever you have cron jobs that produce output, it creates mail. Whenever you have log rotate, well, not log rotate, but log watch, looking at the logs and finding problems, it'll report these log errors or these suspicious behaviors and things you can see to your mailbox. So you can look at it. Why is mail stored in queues? Well, it has to do a lot of waiting and moving. And so you really need it in queues. Where are the print jobs stored? Well, they're stored in that spool directory, right? The var spool cups is our print server. Right now, I don't have the print server configured for any printers. But if it were, you might see some stuff in there. And if I was sending print jobs through, you'd probably see that as well. So why are print jobs put in a queue? Well, printers don't always have enough space for all the print jobs that they receive all at once. And so you send it to a queue, and the spool queue slowly feeds it off to the printer as the printer is ready for another job. So that can be important. Make sure that you don't lose jobs. Otherwise, if you send too many jobs and it can't hold them all, they get lost. So that's why it's important. And that's our little quick thing on system logs and queues.
Linux installation. So we're going to talk about CentOS. CentOS is based on the source code of Red Hat Enterprise Linux, RHEL. The CentOS distribution is community-based, and it does get some support from Red Hat in the form of paid developers. Red Hat pays for Red Hat developers, they also pay for Fedora developers, and they also pay for CentOS, some of the CentOS developers. So where does it fit in the distribution families? There are a couple of different major sources of, well, Linux distributions. You've got the source code based Linux distributions. That would include things like Slackware, which is one of the oldest. You have Gentoo and Arch, and even Android's kind of a source code based Linux distribution. Then you have the whole Red Hat family. Red Hat family includes Fedora, which is kind of their development suite. You have CentOS, which is a version of Red Hat with a lot of the proprietary stuff and branding removed. There is Oracle, which is basically the same thing as CentOS, except it's paid for by the Oracle company there. Red Flag, which is the Linux distribution put out by China. And then there's also things like OpenSUSE. So these are all in the Red Hat family. So they all have a lot of similarities. They all have the same Red Hat package management system. So you can identify them that way. Then there is the Debian family. The Debian family would include Debian. But you also have Ubuntu and Mint. Basically, you have Debian, and some people thought, well, it's kind of complex, so let's make it a little better. And so then you have Ubuntu, which based off that. Then they decided, well, that's a little bit too complex, so they added a little bit more. They gave some more proprietary drivers. You got Mint. And then you have other distributions such as Kali, which is your penetration testing distribution, which also is based off of the Debian family, probably based off of Ubuntu most directly. All right, when you're doing an installation, the first thing that you come across is you have the Anaconda installer. So Anaconda is just the name of the installer. But Red Hat based Linux distributions such as CentOS Linux use Anaconda as the installer. So you'll find that lots of these distributions have an installation wizard that looks the same. That's Anaconda. Anaconda is an installer written in Python. It's got some C parts as well. But it is responsible for making sure the operating system is correctly applied to the machine, put in place. You have the bootloaders and everything else in place, and it boots up. Anaconda works great some of the time. Sometimes it fails. It fails, well, a lot more than the actual Linux distribution will fail when it's running. So you got to be careful with that. Sometimes you have to start over, but that's usually okay. When you're in Anaconda, you have to configure networking. You need to make sure you configure a host name for the machine. Every machine should have its own host name. Don't stay with localhost. Make sure you have a host name. You want to make sure the machine has either DHCP or static manual addresses configured. You can go in there and configure it up. Make sure you have it set. If you do DHCP, you have to make sure that you have a DHCP server in the network it's going to be residing in. If it is not doing DHCP, then you need to make sure you configure all the important parts of static or manual address configuration. You need an IP address, you need a mask, you need to have a gateway, and you need to have a DNS server. Also, after you configure the networking, you want to make sure you activate the interface so that it will come up when you start. You want to make sure you configure the date and time. Well, it's not really date and time you configure, it's more setting the time zone. That's kind of the important thing. You want to make sure the time zone is set. And it's best to set your time zone after you've already configured networking, so it'll automatically decide that you have networking and it will use network time. Network time provides the NTP protocol, or the network time protocol, to allow it to synchronize with time servers and get updates automatically. Normally it saves the time on your machine as UTC time, basically the Greenwich Mean Time or Zulu time. Windows, on the other hand, stores it as local time, so what's written to the hardware might be different for Windows and Linux, and that can cause problems sometimes if you have a dual boot machine or a machine that uses both operating systems. Software selection. You want to make sure you select which software needs to be installed. So when you're starting, the easiest thing to do is to select the GNOME desktop. GNOME desktop will give you all the essentials and get you a GUI, so you can have this clicking ability and the ability to do, well, easier things. However, Linux was designed mostly to be run without a GUI. GUIs have been built afterwards, and they're nice and they can be very pretty, but you don't really want a GUI if you're running a server. So in a production environment, you want to start with a minimal install and just add the features you need and not have everything else, because there are security issues if you have too much. Any software you miss during the installation can be added after, as long as it's not something like network drivers, because you need the network. Installation destination. So Anaconda can automatically create partitions for you, or you can create them manually yourself. So there are two main kinds of partitions you'll see. You can see the standard partitions you can create. Those are your normal fixed length partitions with older style device names, things like /dev/SDA1, which you don't need to worry about. Or you can use the LVM partitions. LVM partitions basically creates this giant, well, Linux volume management partition, and that partition is kind of a standard partition, and then within that you create these blocks that you can then use, and that allows you to be more flexible, resizing and adding things and allowing you to span multiple drives much easier. When you are configuring your partitions, there are lots of different directories you can consider to have as separate partitions. Normally you want to have a root partition, which is the /. You want to have your partition for virtual memory, which is your swap, and you also want to have a partition for the bootloader, the /boot. That also includes things like the kernel and initial RAM disk. So those three are your general three you have. Sometimes you add more. The var directory contains logs, and sometimes you can have problems if your logs fill up and it takes down your entire server, so some people put it as a separate partition to prevent that from happening. When you are done and you start the installation process, you are then given the option to create users. The main user for the system is called root. So root needs to have a password, needs to be nice and secure. The root user has all power as far as the users go on the system and can do many, many damaging, destructive things. You can also have additional users, and additional users are very good to run on the system because they don't have all power, which means that if they make mistakes, they don't necessarily cause as much problems. These users could also be administrative users. So what happens is if you click the checkbox to make it an administrative user, it will add the user to the wheel group. So there are groups, and the wheel group allows members to run commands as root using the sudo command. So you type sudo space the name of the command. It will then usually prompt you for the user's password, and then after that they can run the commands as root. When you are done with the installation, sometimes you see a license agreement portion. If you're doing minimal install, you don't necessarily see it. Sometimes you do. But you need to be aware that Linux comes with a license like any other operating system. It comes with a license. And most of the stuff, most of the packages you get on Linux are distributed under a free software or open source license. Free software licenses require all derivative works be distributed with a similar license. So if you have access to modify it, then this derivative license means that anybody else, when you redistribute it, has the same rights you received. So you have to provide those same rights. Open source licenses allow you to see and modify the code, and that's basically what they do. Now, free software licenses are a special type of open source license, slightly more restrictive, but it makes for more security of the source code in the long run. Once you have your system up and going, you should probably update it. Most Linux installation disks are not absolutely new, and there are updates that, well, need to be applied. So the first thing you should consider doing is updating your updating system, updating software. So you can type in yum update yum. Yum is your updater, so you want to update yum first. Now after that, something you need to keep in mind is that there might be updates that include, well, packages with libraries that are part of your GUI, and you do not want to update your GUI from within your GUI, so you want to make sure you get out of it. You can press the Control-Alt-F2 key sequence to drop into a terminal back place where you can type in commands and not be inside of the GUI. You can also press Control-Alt-F1 to switch back into the GUI. On older versions of Linux or other versions of Linux, sometimes it's Control-Alt-F6 or Control-Alt-F7 to get into your GUI. Just make sure you try a few, you'll figure it out. Once you are outside of your GUI, you want to update your system. So I recommend you don't even log into your GUI until your system is fully updated. But just type in yum update and that will update your system. And that is it for this lecture. Network File System, or NFS. The NFS protocol was developed by Sun Microsystems, which is now Oracle, in 1984. It was built on the Open Network Computing Remote Procedure Call, ONC RPC. It has some open standards. These are RFCs 1094, 1813, 3010, 3530, 5661. So you can look those up and look at the protocol and find information. NFS was originally just a Sun Microsystems thing, and then it went to other Unix distributions, made it to things like Linux and Mac OS X, and eventually to Windows. So it's available all over the place, and it's pretty good. So in order to get NFS running, you need a couple of useful utilities. NFS-utils is a package you can install which provides NFS. You also probably want to have man pages. This is in general for everything. You want to have man pages for, well, reading the man documentation. The NFS service needs to be started after the remote procedure call service is running. If you don't have it running, bad things happen. So on a CentOS 7 machine, you want to do a systemctl start RPC bind and start that service. You also want to make sure that if you want it to start automatically at boot time, you do a systemctl enable RPC bind and make sure it's there as well. NFS should only be started after RPC. Once you have RPC running, you can do a systemctl start NFS server and get the server up and going. You can also enable that one as well to make sure it's running at boot time. Now the NFS server needs to have a list of directories it's exporting. These directories are listed in the etc exports file. So the basic format is you type in your share name, that's the directory location that you want to be exporting, and then you want to decide, well, you list who you are exporting it to. If you want to export it to everybody, you just put a star there, and then inside the permissions you list well, information about what permissions you're exporting it as. So if it's read-only, you do RO. If it's read-write, you do RW. If you want to do something else, you can put other permissions in there as well for the exporting. So once that's there, you can use the export fs command to actually export the directories. Usually you type in export fs space -a to export all of your shares that are being shared in that etc exports file. You can type in the export fs command by itself to then get a listing of which directories are being exported. NFS doesn't really work well if you cannot get through the firewall. So you need to make sure you allow it to get through the firewall. So you go in there and you use the firewall-cmd command, and you give the options. You can give it the -- zone equals public. That's actually optional. It's just default. But you want to do an add -service equals RPC bind, just like it's displayed here. So it's -- service equals RPC bind. That will allow the RPC bind to get through. You also want to add the NFS service through. Now, these are both great. If you then restart your firewall, they will no longer be there. So you want to make sure you use the -- permanent option if you want them to be written to the firewall configuration file and be there after the firewall is rebooted. All right, you can then verify they're there. You can use the firewall-cmd command -- list services to see which services are there. You can also use the firewall-cmd space -- list all command to list all of your firewall rules. I like the bottom one better because it gives me more of a, well, a big picture of what's actually going on. Okay, once again, to make services available at boot time, you need to make sure the system has a proper symbolic link for you to run it. So each run level has a set of symbolic links. In CentOS 7, they have simplified it. In earlier versions with the init, before you had the systemd, you had these, well, 7 run levels, 0 through 6, 0 being halt, 6 being reboot, and 1 being just your basic system, 3 being your multi-user system, 5 being your GUI. And they decided to simplify this down to just a couple. So you got your multi-user one and your GUI one. And what happens is when you use the systemctl command with enable, it will create a symbolic link from that run levels directory over to the actual script that starts. So you just do a systemctl enable and enable your services, the RPC bind and your NFS server. When you want to mount NFS shares, and I would recommend mounting NFS shares as a test before you put it in anything like your file system table FS tab, you want to make sure you can mount them manually. So after the remote server has the shares exported and the NFS server is running and the firewall is out of the way, you can mount the shares. So you just type in mount the remote server's name or IP address, the share or the directory being exported, and then the mount point you want to mount it at. So the directory name of the location you want to mount it to. So if I had, let's say, a friend who was exporting his music files and I wanted to see the music files, assuming this is all legal music files, of course, he might be exporting it from myfriend.com or example.com, and it might be the /music directory, and I might want to mount it into my local music directory. So I might type in mount space example.com /music space /local music, and then it would mount up and hopefully everything would work perfectly and smoothly. Alright, so in addition to just being able to manually mount things, sometimes you want to have it automatically mount on boot time. This is especially important for situations where you have a machine that is getting its home directory from a server. So you can have the server exporting the /home directory. It might be mounting the home directory from the server, and you want to then go into the etcfs tab file and, well, make sure it's mounting. And there is a standard format for all of the mounted partitions. You want to give it the device name, the mount point, the type, your options, the dump number, and the file system check number. The device is the server and the colon and then the share. So if you're going from example.com/home, then the mount point would then be where it's mounted to, so maybe it'd be something like /home. The type would be NFS, and then you have your options, any options for mounting, whether or not you want to allow it to mount smoothly, or if you wanted to make sure it's got this hard mounting, whether or not you want it to crash when it goes down. Usually just defaults. And dump and file system check usually just leave zeros. Anyway, you can read all about using the FS-tab file and the formatting in the man pages, which you should have because you have installed the man package. When you're troubleshooting, you want to verify that your IP address is correct. So go take a look at the IP address, make sure it's correct, make sure the IP address of the server is correct, make sure you are in the same network, things like that. Verify that the services are running. You want to make sure the server is exporting everything, it's running. You can use netstat, you can use exportfs to make sure it's exporting. Verify the firewall is on the way. You can use the firewall-cmd --list-all command to see what's actually being allowed through the firewall. You want to make sure that the remote server is up and you can ping things. You can use tools like nmap. You can install nmap and use that also to verify ports are available when you're scanning the remote server. So good luck with your NFS installation. Samba. The server message block SMB protocol was originally designed at IBM for use in DOS operating systems. Microsoft started working with it in 1990 and has incorporated it in Windows since Windows 3.1.1, which was Windows for workgroups. The Samba package implements SMB and uses it for communication with Windows devices. The SMB protocol has many security concerns. The SMB protocol has received many security updates since Windows Vista. However, it is known to be a security risk because of older implementations and even some newer bugs. We can use SMB to hack into Windows XP and Windows Server 2003 machines. With Windows XP, all you had to do was have file sharing ports open through the firewall, or just have your firewall turned off, which was very common for gaming back in the Windows XP days. Windows Server 2003 came right out of the box open for attacks and complete takeover through the SMB protocol. Many major companies, including Sony, have been hacked through the SMB protocol. There are a lot of useful packages in Samba. On the Samba set, there is the Samba package, which installs Samba and dependencies. You have the Samba client, which provides the SMB client, which allows you to navigate through remote Samba share and download and upload files. You have CIFS utils, which allows you to mount Samba shares, and you can even set it up so they mount automatically in your FS-tab file. The Samba service can be started using the systemctl command. You just use systemctl start SMB, and it will start the Samba server. You can also stop, restart, and check status. If you wanted to start at boot time, you just use the systemctl enable smb.service to enable it. In order to allow other machines outside of your individual server to mount your Samba shares, you need to open up a hole in the firewall. So the easiest way to do that is to add the Samba service. So you can use the firewall-cmd command. You can add the zone if you want. Then --add-service equals Samba. You can verify the service is present in the firewall using multiple commands, my favorite being the bottom right there, which was or is firewall-cmd space --list-all, which will list all of the services that are available through the firewall. When you want to configure Samba, the main configuration files are found in the etc Samba directory. The most important of those configuration files is the smb.conf. You might be able to find a file like smb.conf.example, and you might want to copy that over the smb.conf file before you start editing, and then you can go in and set all kinds of configuration settings because they'll be available and easy to see. Here is an example of an excerpt of, well, part of the smb.conf file. We have a share called software, which is being exported. That share is based on the /share/software directory. So whatever files in that /share/software directory are being exported. When that directory shows up on a remote machine, it will be called Windows Software Packages. It is public, so you can see it. It is writable, so it's read-write, but it is not printable, so it's not a printer. So that's the information you see right there. When you want to share your Samba shares, you might have issues with SE Linux and their context. SE Linux is very good for protecting you from very bad mistakes you might make, but files shared using Samba should have the correct SE Linux context type of a Samba_share_t in order to be able to be viewable by the Samba service. To change the context of the file, you can use the chcon command, which is change context. So chcon -t for the type, Samba_share_t, and then your file name or directory name, and it will change the context type so that the Samba service can see the file. If you're having trouble with Samba, it's good to verify the IP addresses are correct. You want to verify the services are running. You can use netstat to view that. You can verify the firewall is not in the way using the firewall-cmd space --list-all command to see which services are allowed through the firewall. You can verify the SE Linux context is set correctly. You can use this ls -Z or ls-al-Z, and that will tell you the context type of all the files in the directory. Or you can just do ls-Z of the file to list its context type. If it's a directory, you want to add a D in there. So there's all kinds of things. You can verify the remote host is up using ping. You can verify remote ports are open using nmap from a remote machine. And you can also check the logs to see what's happening. And that is your overview for Samba. Apache Web Server. The Hypertext Transfer Protocol, or HTTP, was created by Tim Berners-Lee and his team. They proposed the World Wide Web project in 1989. They had a first working version in 1991, and then the RFC that defined it, RFC 1945, was in 1996. However, by the time many web browsers were already out there and people were using the web. There are multiple RFCs, including 2616, which is for the HTTP 1.1 protocol. The HTTPS protocol, or the Hypertext Transfer Protocol Secure, layers the HTTP protocol on top of the SSL and then now TLS protocol. So SSL 3 is the same thing as TLS 1, so basically it's just kind of transferring over to the newer ones. So you want to make sure you have TLS, not SSL. It was created by Netscape Communications in 1994 for the Netscape browser. So the Netscape Navigator browser, and used, and everyone else started using it. it created an industry for signing digital certificates. So many companies were able to make money off of this, including the Ubuntu project was funded by Mark Shuttleworth, who made his money off of this as well. HTTP security concerns. There are some concerns you should think about. All communication over HTTP is plain text and easily sniffed or wiretapped. People can read it. They can also inject their own stuff into it. Some ISPs are starting to inject ads or JavaScript into your sessions and break things, and that's always nice. Gotta know who your ISPs are. Web servers and web browsers cannot prevent programmers from making mistakes or malicious users from exploiting these mistakes, so you have to keep that in mind. The HTTPS protocol also has some security concerns. There are various SSL and TLS protocols with different levels of security, so you need to keep that in mind. If you get a browser that allows you to have keys of size 0, that's not so good. You just need to make sure you know what your browser allows, and if you're running a server, know what your server is serving. Certificate authorities are sometimes exploited and used for further exploitation, so you need to be aware of that. And then government agencies such as the NSA have promoted protocols with secret vulnerabilities, such as random number generators that don't produce random numbers. Some useful packages include the HTTPD package, which provides the Apache web server. You have Links, which is a text-based web browser for testing things if you are not running on a GUI environment. Sometimes you want to test things from the server, and Links is pretty good for that. Also, OpenSSL, which allows you to make certificates. You can also sign your own certificates. You can get the certificate signing request. You can then use and send to a third party who will sign them for you. So OpenSSL will do that stuff for you. Mod SSL will allow you to integrate into Apache the HTTPS functionality and then serve secure web pages. The Apache web service can be started using systemctl. You can use systemctl start HTTPD. You can also stop, restart, check status, and also you have this reload option. Reload is interesting because what it does is it will send a signal to the server. The server is then prompted to reread its configuration files, and the server is actually multiple servers running, and when you send this over, the main service can reread the configuration files and respawn new children, and then just let the other children, well, kill them off. And then you won't have to worry about it anymore. So you can keep your server running while you change configurations, which is kind of nice. There are some other issues. Whenever you want to connect to your web server from the outside, you need to get through the firewall. The firewall is not open by default for the HTTP and HTTPS services, so you need to open those up. You can do that with the firewall-cmd command. You just need to use the --add service equals HTTP or HTTPS options. If you want it to be permanent, you can use the --permanent option as well, and that will make it so the firewall is open and, well, permanently open. You can use the firewall-cmd space --list all command if you want to see which firewall rules are in place and which services are available, so you can know if you will be able to get to the firewall. The main Apache configuration files are found in the /etc/httpd/conf directory. Also, you have this etc httpd conf.d directory, which has these other configurations such as user directories and SSL configurations. But the most common file you'll work with is the etc httpd conf httpd.conf file. This httpd.conf file is the main file, and there is a directive in that file that loads all the other files in the conf.d directory. So in that directory, you can, in that file, you can configure your Apache web server, tell it which ports are open. You can tell it whether or not it allows certain types of data or other types of pages, such as server-side includes and CGI. You can turn those things on or off. You can also change which directory index files are used when a file is not specified within a directory. So normally that's index.html, but you can have it be index.cgi, index.php, index.shtml, many different options. So you also have a directory setting in there where you can change where the directory root is, and you can also change your document root. Your default document root is your var www.html directory, so you can go there and see your web pages or set your web pages. When you are creating web pages, there are a couple of SE Linux context types you should be aware of. The following are some that are used by Apache. You have this httpd_sys_content_t, which is used for regular system-wide web pages when you're serving web pages for your web server. You can also use CGI scripts, and I like CGI scripts a lot, and so I think it's very important for me to know the httpd sys script exec t type, which you have to set on all of your CGI scripts, as well as setting your execute permissions or execute bits. If you are not in the normal system directories and you are in userland, well, all this userland, but in home user directories, and you've turned that on in your user dir configurations, then you can use this httpd user content t or httpd user script exec t and keep those in mind. In addition to those types, you also have types for directories, whether or not you are allowed to upload files or not upload files, and so just keep that in mind. Troubleshooting. So when you are having trouble with your Apache web server or web pages, it's good to first verify your IP address is correct. Sometimes it isn't correct. Sometimes you have DHCP. You want to make sure you have a static IP address, or if you're doing DHCP, that's fine too. But verify the services are running. You can use netstat, and you can check to make sure they're there, and listening. Verify the firewall is not in the way. You can use the firewall-cmd space --list-all command in order to verify the firewall is not blocking anything. Make sure it's open. You can use the SE Linux commands. You can use the ls-al capital Z in order to see the context types of files and make sure they are correct. Sometimes this is really important in a situation where you have SE Linux running. You have all your permissions set correctly, and you think a file should be available, but Apache just can't see it. So SE Linux. Also, that tends to throw up SE Linux, errors in the audit log. So you can go to var log audit log, I believe, to look at the audit logs. You can also verify to make sure the remote host is up, and you can ping it. You can use nmap to scan it, make sure the ports are open. You can also check the Apache logs, so var log httpd, and make sure the access log and error logs don't show anything, or if they do show something, use that to troubleshoot. And you can also check system logs and see if you have trouble starting the Apache web server. And that is the end for this presentation. Database servers. MariaDB is a database based on an older MySQL database. It was also created by the same people. MariaDB is a drop-in replacement for MySQL. MariaDB is a relational database management system, so that's RDBMS, and implements the structured query language, or SQL. So here's a little bit of the history. So MariaDB, it's kind of a fork. First, MySQL was created and replaced Oracle in many projects, especially in open source. Oracle was not very happy with this, and it wanted to do something to solve the problem. So there was a time when MySQL was not financially able to continue on, and so that became an issue. So Oracle was trying to get rid of MySQL, and it acquired multiple companies that provided libraries to MySQL, and that was a bit of an issue. Eventually, Sun Microsystems acquired MySQL, did the whole white knight thing, and saved it from Oracle takeover. However, a little bit later, Oracle discovered that they could grab MySQL, Java, and other things all at once, and they bought Sun Microsystems. Eventually, the developers of MySQL decided to fork the MySQL code, and they formed MariaDB. The current versions of CentOS use MariaDB as the database. There are a couple of MariaDB security concerns. First of all, the default MariaDB installation does not have a root password, so you can create users, database, tables, all without setting up a password. Also, this might not be a major security concern, but administrators can reset the root password for the databases and get full access if they want to. It might actually be a helpful thing if you lose access to your database and you can't get back into it. The root user can then help you get back into it. There are many useful packages. There is the MariaDB, that is the client programs, the MariaDB server, which is the server, and then there is the MySQL-Python package, which provides a way for the Python language to communicate with the MySQL or MariaDB servers. Generally, the configurations for MariaDB are just fine and you can leave them alone. However, if you do want to go in there and make some kind of a change, you can go into the etc/my.cnf.d directory, and you can find configuration files in there you can mess with. The standard format of the configuration files is a name equals value pairs. For example, you can type in port equals 12345, and you can change which port it runs on. Here are a couple of sample MariaDB commands. So from the command line, you can type in MySQL to get into MariaDB. You can also do options such as -u and the username, or -h and the host name, and -p to prompt for a password. And this will get you into the MySQL or MariaDB databases, depending on which one you actually have installed. So once you're inside, you can create databases. You can just type in create a database and then the name of the database you want to create. And then to actually use that database, you use the word use and the database name, and it will change your prompt and indicate that you are now inside of that database. Once you're inside the database, you can create tables. So here's an example: create table people, which gives it 2 columns. You have name and age. Name is a primary key and it is a varchar 250, and age is an integer. So with those tables, here are a couple of sample SQL statements. You can insert values into that people table. You can update the people table and replace information. You can do select statements to pull information out, and you can also delete records from the table. So these are the 4 basic commands. You have insert, update, select, and delete. There are other commands, obviously, but those are the main 4. You can also do things like insert into the table, and then if there are duplicate keys, you can just update instead, which is very common for things like logs, and so I do that quite a bit. So if you're using Python and you want to do programming, here are a couple of pieces of, well, a bunch of code examples thrown together onto one page. You want to import the MySQLDB library, and you want to make sure that you pay close attention to case here, because the case is important. You want to connect to it, and then once you connect to the database, you want to create a cursor. A cursor is where you send your commands. So you just send your commands, you can execute the SQL statements, and after you've executed the statements, you can sometimes grab back data. If you make changes, so inserts and deletes, sometimes you want to commit that, and that is committed not with the cursor, but with the actual connection. And then when you want to close, you can close the connection itself. If you're trying to troubleshoot MariaDB, you want to make sure your IP address is correct. If you are going to a different machine, which is not usually the case, but you could, you want to make sure the services are running. If it's not running, it's very difficult to connect to the database. You want to verify the firewall is not in the way if you are going over something. Normally, people just run it on their local machine and they use Apache to actually get out. So you're interfacing with a web server, and the web server is talking directly to the database. And so the firewall is not an issue. You want to make sure that any SE Linux stuff is not changed. If it is changed, you go and verify things. You want to make sure if you're going to remote machine that the host is up, and make sure that ports are open if they need to be. And if there are any problems and you can't figure it out, just take a look at the logs. Most of these things only matter if you are using a remote machine, which is very unlikely. Anyway, this is your MariaDB or database overview. Secure Shell. The Secure Shell or SSH protocol was created in 1995 to prevent sniffing of Telnet and RLogin traffic at Helsinki University of Technology. SSH is encrypted, and Telnet and RLogin were both not encrypted and still aren't encrypted. So the SSH protocol uses the Diffie-Hellman key exchange for key generation that it then uses to symmetrically encrypt data. Many programs use SSH to create tunnels and transfer data securely. The SSH package is normally, or the packages are normally installed on a CentOS or other Linux system by default. However, if you want to install them or take a look at them, they are the OpenSSH server package, which provides a server, OpenSSH, which provides some of the tools, the OpenSSH clients, which provides, well, clients, and then another useful package, which is not actually SSH, but is closely tied to it, is rsync. rsync allows you to synchronize data on two ends, so a client and server can synchronize data over SSH. Or it can do it itself without SSH as well. When you're configuring SSH, there are a couple of configuration files. The main SSH configuration files are in the following two files. You have the etc ssh sshd_config, and the same thing without the D. The one with the D is for the server, and the regular one, the ssh_config, is for the client. Individuals can also have additional override type information for their clients in their .ssh directory of their home directory. So some common configuration changes you would see on the server end is disabling root logins, which is very important in situations where you're constantly being attacked by people trying to log in your system. If you don't want them to have the option of doing a brute force login, you can just disable root logins, and then they have to log in as a different user and then switch over somehow using sudo or su. You could change the port number. Sometimes people change it from 22 to something else, and then they log in with that number. You can disable password authentication, which means you have to use keys to get in, which makes it more secure. This is very common. Amazon Web Services does this by default. It makes it more secure and less likely to be hacked because, once again, you can't do the brute force logins. And you can also do changes to things like X11. X11 is your GUI system. You could set it up so that you can export your GUI or not export your GUI. The Secure Shell service. So SSH is on Linux systems OpenSSH, and it can be controlled using the systemctl command. You can use systemctl with start, stop, restart, status. You can enable or disable if you wanted to either not start boot time or not start boot time. And so systemctl start, and then the service name, which is sshd, and you can use the .service if you want. By default, SSH is allowed through the firewall. To make changes, you can use the firewall cmd command, and you can either add the service if it's not there, you can remove the service, or if you want to, you can, well, additionally, you can make the rules permanent with the -- permanent. Note that if you use the -- permanent option, it will not change the active firewall settings. It will only change the configuration files. So when the firewall is restarted, it will have the new settings in place. You can verify the services are present in the firewall as well using the firewall-cmd command with the -- list -all option to see what's in the firewall. When you connect to unknown servers, SSH prompts you to accept the public key that it is presented with. Keys are remembered and stored in a file called known hosts, and remote keys will change very rarely. It's only when the machine is replaced or new keys are generated, or if someone's trying to hack you and there's some kind of a man-in-the-middle attack where they're trying to impersonate the server. You can manually add and delete entries. This is useful when you trust the changes, but not so good when you don't trust them. SSH has the ability to use keys to authenticate. In order to authenticate using keys, the client machine needs to create a public-private key pair set. The public key needs to be installed in the server, and the server has a authorized key file in each user's directory that can be used, and then you can just log in directly using the authorized key. You can create the key pairs using the SSH keygen command, and then you can install them either using the SSH copy ID command, or you can manually copy them over and then put them into the authorized keys file. Here are a couple example incantations of things you can type in. You can type in SSH keygen to generate keys. You can tell it what type with the -t option. You can copy the key over, the public key over to the server using the SSH copy ID command. You can manually copy it using SCP, and once you get it copied over there, you need to log into that machine and use the cat command or some other command to get it into the authorized keys file. If you want to, you can also tunnel. Here are a couple of exciting tunneling incantations. The tar command can create, well, archive files. And this command, basically the first command right there, you're creating an archive file, and the destination of that file is actually the standard out. So that kind of works. And then what we're doing is we are piping this into the SSH command, which is then on the other end using the cat command and redirecting its standard into a file. So what we're doing is creating a tar archive that is being put into a file on the remote machine. And you can look at the rest of these things. They are kind of weird incantations, but it gives you an idea of some of the things that SSH can do. If you want to troubleshoot SSH, you want to make sure that you can connect to the machine. That's usually one of the biggest things. You could either have the address wrong, or you could have the host name wrong. You want to make sure the service is running. If it's not running, then that can be a problem. You want to make sure the firewall is open and you can get through it. You want to make sure the remote host is up, and so you can ping it. You can use Nmap to scan it to make sure the SSH port is visible. And you can also be on the server and look at the logs to see if you're having trouble logging in. And this is a brief little overview of SSH. Mail servers, most specifically postfix. So the Simple Mail Transfer Protocol, or SMTP, was published as RFC 788 in late 1981 by John Postal, who is considered the god of the internet. John Postal produced many different standards. Lots of different RFCs have his name on them, especially the early ones. He disappeared toward the end because he died. But He was one of the founding inspirational members of the creation of the internet. So this SMTP protocol uses plain text commands to communicate with remote servers listening on TCP port 25. You also have webmail and application client programs that send mail. And what happens with those is you have this front end, but you still have a mail server in the back end. So this local mail server that handles all the communication with the remote servers. It sends and receives them, and then use the webmail or application clients to retrieve it from the server and send it to the server. There are many different directories involved with these mail servers. The etc postfix directory contains all the configuration information for the postfix server. You have the var spool mail directory, and that one contains all the email that has been received and processed and put into users' files. So there's an mbox style file. Basically just lists all the email messages one after another in one long text file. So you can go there and grab the mail messages for each of the users. And then there is these var spool postfix directory, and that's where postfix stores data. It's acting as a server, all the incoming mail, outgoing mail. It stores them in different folders. There are lots of things in the protocol, such as the ability to retry sending mail when the server's down and other things like that. And so it has to maintain and hold things that are still on their outbound direction. Also inbound as is processing and looking at things. The var log mail log file is a log that can be used to troubleshoot email related problems. All kinds of things show up in there about the mail server and mail messages coming in and out. There are some SMTP security concerns. First of all, plain text messages can be viewed in transit. So if you are sending or receiving mail, anybody along the way between the source and the destination could look at the mail and read it. Now, that doesn't mean you can't encrypt your message inside of your mail, but the header data would still be unencrypted. So you have to keep that in mind. All of the messages are plain text. If the message itself is encrypted, that doesn't mean the headers are encrypted. Anyone can send unsolicited messages at a very low cost. So spam is very cheap. You can send all kinds of mail. You can claim to be anybody you want. There are a lot of different changes in how mail servers are handling this. And so they can look at things and say, well, you're claiming to be from one server, but you're actually sending it from a different server. And then they can mark you as spam. And there are other things they can do to try to filter things out. Also, the protocol allows for things like relays, which make it easier to spoof sources. So you can send mail messages through a server. Most mail servers now are configured by default to not allow relaying, but relaying is still possible and it can still be turned on. The messages themselves can carry malicious files or content. You got things all the way back to the I Love You virus that was hitting people's machines and then being processed locally and causing all kinds of problems, to more recent malicious things. You can have all kinds of tricky messages. You can have messages telling you about a Nigerian prince or selling you things, claiming to be somebody they're not. And yeah, those are bad. And rejected messages can be used to perform directory harvesting attacks. They can just send email messages to everybody in your system and then decide which messages get bounced and which ones don't. And the ones that get bounced probably mean there's nobody there. The ones that don't get bounced, well, they probably mean there's somebody is there. So you can use that to find who's on the system and then use that information to then try to log into their account by guessing passwords and things like that. So some of the useful packages, Postfix is the SMTP mail server. You have other things that are related. Dovecot, which we will not talk about much, does provide your POP and IMAP servers. So Dovecot's a nice thing to look at. Telnet Telnet is a great terminal emulation program that allows you to connect to ports, and you can use it to telnet to your local host port 25 if you want to walk through the mail protocol and try to figure out what's going wrong. Alpine is a great email client. It comes from, well, it's based off of Pine, which was based off of Pico, and Nano is based off of Pico. So you get this kind of thing happening here. Anyway, Alpine is a great text-based email client, and you can use it, but you have to first install the EPEL libraries. So if you don't have the EPEL-release package, you'll need to get that in there, and then get Alpine. Postfix is available and running on default CentOS Linux 7 machines, but it is only listening locally. So it's receiving local host type email messages, and some of the services use mail as a way to communicate with the administrator. So one example would be the cron process. Whenever there's a cron job that produces output, it will send an email message to the user root, indicating what the output of the command was. So normally you write cron jobs that have no output unless there's an error, and then they produce output and it gets emailed to the administrator. But if you wanted to do more than just listen locally, you need to make some configuration changes. So in order to configure postfix to allow external connections, you need to edit the etc postfix main.cf file and allow listening on all interfaces. So you can scroll down a little ways through that file until you find a section with 4 lines. The top line would be the inet interfaces equals all, which will be commented out. You need to uncomment that one. And you want to take the one that says inet interfaces equals local, and you want to comment that one. Now, when you uncomment it, make sure you just remove the hash mark. Don't remove it, leave a space there or something like that, because then it won't work. So make sure you do it correctly. And then, once again, you have to restart your service. So if you want to restart your service, you can use the systemctl command. So systemctl start postfix.service. You can do systemctl with a start, stop, restart status to start, stop, and restart, or get the status of your service. You can also make sure it starts on boot time with an enable, or make it not start on boot time with disable. Now you don't need to worry about enable and disable because it should be running already by default. Once again, because it comes pre-configured that way. In order to receive mail, the mail server must be obviously listening, but it also needs to be allowed to receive communications to TCP port 25 from outside machines. So in order to allow inbound TCP 25, you can use the following command. Just use the firewall-cmd space --add-service equals SMTP, which will allow the SMTP protocol to come through. Well, allow port 25 to come through. You can then verify the services are present in the firewall as well with the firewall-cmd-list-all command. And once again, if you want to allow your service to be there after a restart of your firewall, you'd want to add the -- permanent option to the top command so that it gets stored into the firewall configuration files. So when it boots up, it will automatically add it there. One more thing to think about, external email service identification. So Postfix and other email servers follow standard protocols, which is nice, but it's also kind of confusing sometimes. In order to send email, the Postfix server uses the host domain part of the email address to identify the server. So if it's a bob@example.com, it's going to check first for a DNS record for an Amex record for example.com. If it does not find it, it will check for an A record in the DNS service. And so it looks for example.com, and if it finds an MX record, it will use that. If it doesn't, it will use the A record, and if it doesn't find that, it will not send the mail. So it does not use the etc host file. So don't try to make that work. It just doesn't work. It refuses to do that. So you want to make sure you can use your DNS service, which means you have to have it configured. Troubleshooting. So if you are having trouble sending mail or receiving mail, you want to verify your IP address is correct. You want to verify the services are running. You have your mail server running and up and going. You want to verify the firewall is not in the way. You want to verify that DNS records are there so that it knows which server to identify and use. You want to make sure the remote host is up and you can ping it to do that. You also want to verify that the remote ports are open, so you can use Nmap to scan the machine, make sure port 25 is open. You want to make sure you can check logs. So you can go in that var log, mail log, and take a look at that. You can also check the mail directory and see if mail is being received. So here are a couple of things, and that is our mail server or postfix mail server overview. Dynamic Host Configuration Protocol, or DHCP. So the DHCP protocol operates on UDP ports 68 and 67. DHCP is based on a series of messages. You have a discovery message, an offer, request, and acknowledgements. So what happens is a client will come online and they will send out a DHCP discover packet. Then a DHCP server, assuming it sees it, will then offer a DHCP offer. And they offer an IP address that the client could then potentially use. It is then up to the client to collect all the offers it receives, decide usually the first one that comes, but which one they're going to accept, and then they're going to request that of that DHCP server specifically. After it has been requested, the request will be sent out broadcast so that all the other DHCP servers who made offers will see the request, and then the acknowledgement comes back, letting the client know that the request has been acknowledged, and they can then start using that address. In addition to that, they will get a lease, so they get a certain amount of time they can use this address, at the end of which they will have to renew, well actually somewhere in the middle they will renew their lease, but at the end of which they would lose the address. So some security issues with DHCP. If you have rogue DHCP servers, they can give out addresses, and that can be a problem. It could mean security issues. It could mean someone's giving you something incorrect. Sometimes you'll have someone plug a wireless access point, some kind of a home router, in your network backwards, and it'll start issuing out addresses. You can block that on the switch, but if it's not blocked, they can cause all kinds of havoc. Clients can spoof MAC addresses to gain additional access. So if you want to get access and you know that a specific IP address gets it, or a certain MAC address gets it through the firewall, you can spoof addresses. And this isn't really a DHCP problem so much as an issue with MAC addresses and security and everything there. But you can spoof things and get more access. Clients can also obtain multiple IP addresses by presenting multiple MAC addresses. So if you have a client that is trying to create a denial of service type situation, they could present a whole bunch of different MAC addresses, get a whole bunch of different IP addresses, and then lock them all up so they're not available to anybody else. Some of the useful packages. The most useful package here is the DHCP package, which includes the DHCP server, which is DHCPD. There are other ones that are there. You have a DHCP libs and DHCP common, which are used basically in order to get DHCP in the client to run. So the directories that are interesting, there is the etc DHCP directory, which contains all of your DHCPD configuration files. So you can look in there and see what's there. You have your network configuration, and those are in the etc sysconfig network scripts directory. All of them start with the ifcfg, and then it's usually -eth0 or ens32 or something else. So you have to go look and see what interfaces you have, and then you can go configure those. If you're running as a DHCP server, you can see the varlib dhcpd dhcpd.leases file, which will contain all of the leases you've given out. You might note that there are multiple copies of the same lease that's there, because sometimes a client will request something more than once. It might go down, come back up again before the lease is expired, and it might get a new renewed lease. Anyway, that leases file keeps track of all your leases for you. And then there is the var log messages file, which contains all kinds of information, such as all of your discoveries and offers, and all those things can show up in your var log messages file. So the configurations for the DHCP server are in the etc DHCP directory. The following is example dhcpd.conf file. You can see right there on the top, you have the option domain name. You tell it your domain name, option domain name servers. You tell it what DNS servers people are using to get out. You tell it a default lease time. This one has 300, which is 300 seconds. A maximum lease time, which right here is 1200 seconds. So these are very short-term leases. So a default lease of 5 minutes with a maximum lease of 20 minutes. Obviously, you want to have much, much longer times, but they're in seconds. The subnet right there, you can see we have a subnet being configured to give out information. So this is the 10.10.0.0/16 subnet, and we are handing out addresses in that subnet only to 10.10.0.100 through 10.10.0.150. So there's only 51 addresses that are being handed out, and then we're telling them that their default gateway is 10.10.0.1. So that is the routers is your default gateway. You can also, in addition to just giving out a range of addresses, you can give out static addresses. So the DHCP server can be configured to assign the same IP address to a machine using the MAC address. This is very common in situations where you have a machine that has to come up with the same address every time because it provides services of some sort. The following example to assign a printer. So the printer had the MAC address of 00:11:22:33:44:55, and then you could have a fixed address of 10.10.10.10, and that would be the information you give out. And so you put that inside of that subnet section on the previous slide to make sure it gets that information, and also to make sure it still gets the router information and DNS information. The DHCP service needs to be started in order to start listening. You can use the systemctl command to start the DHCP server. So you do systemctl start dhcpd.service to start it up. And other options you have is stop, restart, status. If you wanted to start at boot time, you can do enable, and then you can do disable to make it not start at boot time. Having the service running won't guarantee you can get anything. You still need to make sure you can get through the firewall. And in order to receive requests, you need to make sure that the ports are open. So you really need to be doing both, because it sends out and receives on different port numbers. But you can use the firewall-cmd-add-service equals DHCP command to add the DHCP service to your firewall. If you want to be permanent, once again, you need to make sure you add the -- permanent to the end. So firewall-cmd space -- service equals DHCP space -- permanent to make it permanent and make it there when you start it. You can verify the services are present in the firewall as well with the firewall-cmd space -- list all command, and that will get it there. Once you have your server running, you can go check your messages and stuff like that. But if you're having problems and clients aren't getting things, you can go troubleshoot the clients first. If it's a physical connection, you want to make sure that you have the clients there. You make sure the clients have NICs and cables, and you can use the lspci command on Linux to verify to make sure you have a NIC driver. That can be important. You can verify the server address is static. So your DHCP server must have a static address, otherwise it will not work properly. It doesn't work off a DHCP, so don't try. And you want to verify the firewall allows connections, so you can look at that. Verify or look at the logs to see if there's anything in there. Check the leases to see if it really is giving out leases, or if they're being handed out. if you are setting up a network, you can actually have your configuration have multiple different subnet sections. And then if you have multiple subnet sections, you might be servicing different subnets based on information being forwarded. So you want to verify the routers forward the request. If they need to do that, you want to verify the spanning tree is not a problem. Sometimes spanning tree is configured so that a machine booting up will be assumed to be a switch, in which case it will block everything until it is determined that the machine is not a switch, and then it will allow communication through. So you want to make sure the spanning tree is not blocking anything. And you want to make sure that the switches are allowing you to answer, so your machine needs to be connected to an interface that is allowed to send out your DHCP offers. So you can receive the discoveries, but you can't make an offer unless, well, you can make an offer, but your offer won't get out unless the interface is allowing you to get out. And so you want to make sure that the switches are not blocking you from making offers. And that is the end of this section. So good luck. Domain name system, or DNS. The DNS protocol converts names to IP addresses and vice versa. It also does names to names and other things as well. But it solves some of the problems of the host file because the host file was getting too big. There was at one point a single host file, and people would send their submissions to the maintainer of this host file, and the maintainer would update this host file, and then people would download copies of this host file, and it became a regular full-time job basically. And so the DNS protocol was basically invented as a solution to this problem. How do you maintain this giant host file? So it became a hierarchical database of information. It was invented in 1983 and 84 and has been in wide use since the mid-1980s. The DNS protocol operates on both UDP and TCP ports 53. UDP for your normal inquiries and TCP for your downloads of zone transfers and things like that. There are a couple of DNS security issues or concerns you need to think about. If you send spoofed responses while making a request, the DNS server might get confused and keep your entries. Basically, the way this happens is you send a request to your DNS server. Your DNS server, if it doesn't have a cache, will have to go to another server to get the information. So it sends the request. If you know where it's sending the request and you can spoof that source address, you can send a reply as if it were coming back from the server that it requested from. And if you do it fast enough, your reply will get there before the actual reply from the server it's requesting it from, and then it will get loaded in the cache of your DNS server and cause it to have incorrect data. The next concern is that alternative DNS routes can redirect all of your traffic. So it's a hierarchy, and it starts from the root servers, which delegate to servers that manage the top-level domains, and those delegate to individual servers that manage domain names and things like that. If you modify the DNS route, you can redirect all of the traffic somewhere else. So some countries have done this, and such as China did this for a little bit, might still be doing it. Other countries have done this where they have created their own root servers and redirect everything. In addition to redirecting traffic from the root servers, you can also do DNS manipulation by ISPs. Your ISP controls all of your traffic. They can manipulate your traffic. So if you send a request out to a DNS server and your ISP decides to modify the DNS query or response, they can do that. Also, there is registrar-based DNS manipulation, because the registrars are where the individual domain owners have their data stored, and those could redirect and point to different places. You can also trick registrars into transferring names over to you, and it can be all kinds of a mess. So on Linux, we tend to use the bin D DNS server. Usually you'll hear about it being bin D, bind, or name D. Anyway, there are a couple of things to think about. all host names end in a trailing dot. Normally when you see a host name, you don't put a trailing dot on it, but the DNS server knows it has a trailing dot and it puts it there. So you need to be aware of that, because bind treats it like it should be there. Host names and IP addresses in DNS are written with the largest grouping on the right and the smallest on the left. What does that mean? Well, if you look at a name like example.com, com is a much larger grouping, and so it's on the right hand side. Example would be on the left hand side because it's smaller. So the larger it is, the further to the right. But if you think about IP addresses, something like 10.11.12.13, and you say, well, which one's the largest grouping? Well, the 10 is the largest. So it's on the left-hand side. But that's not where the DNS wants to put it. It wants to put it on the right-hand side. So if you were to write out your 10.11.12.13 in a DNS type format, it would actually be 13.12.11.10. And then it'd have a dot in adder.arpa. So keep that in mind. Also, some types of records have a single value and some have more than one value. MX records have a priority and a value. So an MX record will take a name, usually a domain name, and then it will give you a priority, and it will also give you a host name of a machine you can talk to if you want to send your mail. In addition to that, there's things like the SOA records and other records that have multiple different pieces in them. Some of the useful packages in installing bind, well, you have bind and you have bind-utils. Bind-utils is really good. It provides all those really important tools like NSLOOKUP and dig, which are good for, well, doing DNS queries. You want those. When you are configuring your bind server or named, the main configuration file is in the etc directory, etc named.conf. So you go in there, you modify that file. Sometimes it's etc named, then named.conf, but you find the file there, you modify that file, and that file lists all of the data that you need to know about. So where is the data stored? Well, the data is normally stored in the var named directory. So you have the var named data, which would be all of the zones that you control. And then you have var named slaves for all of the zones that are acting as secondary or slave zones. And those would be zones you get from somebody else. Now, there is a big push for renaming things. And so while it is var named slaves right now, you'll probably find that words like master and slave will start to disappear because they have a negative connotation. So just be aware that the name might change to something like secondary or something else. What does the named.conf file look like? Well, you have different zones in there. There's lots of data in it, but you have these little entries for your individual zones. So that top one right there is for the domain.ext. So you could have a example.com zone, and then inside of it you have, well, information about that zone. This one, because we own it and we control it, we have the type as master. And then you list the file. Where's the file? Where the file is going to be called domain.ext.zone. And where would you find that? Well, you're probably going to find it in the var named maybe data directory, but you have to look at the rest of the configuration file to figure out where things are actually stored. All right, if you look at the IP addresses, let's say we were doing something for the 10 dot range. We want to do the entire 10 dot range all in one file, which is quite a bit actually. So you might do zone 10.in-adder.arpa. And that would be the zone that you'd be doing. And you'd have it be a master because you are controlling it and configuring it. And then the file type would be, or the file name would be something like your IP address .zone. Now the file names don't have to match the backwards orientation or anything like that. So you could just put 10.0.0.0.zone. It doesn't even need to add an end in the word zone, but some editors treat different files differently depending on the extension. So that's something to keep in mind. So you have forward zones and reverse zones. A forward zone is a zone that uses names as its lookup. A reverse zone is something that goes from IP addresses back to names. So forward zones have multiple different types of records in them. So here's an example forward zone with, well, a bunch of things, a bunch of variables and so that. But we can see the very top line right there is a $, then TTL 3H, which basically means your time to live for each of your entries is 3 hours. That's the default time, but it can be overridden and changed. And then you can see the @ sign. The @ sign means for the entire zone. So @ in ns dns.domain.ext dot. You see that trailing dot? That's important. So basically what this is a record for this zone, and this zone is defined as whatever's in the named.conf file. It's saying that the name server for this zone is dns.domain.ext. Well, you're going to need to make sure you have this dns.domain.ext defined somewhere. So we're assuming this is the domain.ext file, and you can see at the very bottom line there is a DNS in A, and then you put the IP address there. And the IP address right there is written in normal IP address format, so it'd be 10.11.12.13. No trailing dot in that one. So what you have is the word DNS in the front of that line, and then your IP address at the end. And if there is nothing after the DNS, no trailing dot, it assumes that you are just giving an address in that domain. And so if this is domain.ext, it will assume that is dns.domain.ext dot. And that would satisfy the name server record at the top with an A record at the bottom. Inside of each domain, you have a start of authority type record and SOA. And each one of these records has a couple different pieces. You can see the domain that it's doing everything for is the domain.ext, and then you have this root.domain.ext. Well, what is that? That's actually an email address. You don't see the @ sign in the middle of the email address because the first dot is supposed to be replaced with an @ sign when you write the email address. So it actually be root@domain.ext dot as the email address for the administrator of that record. And then you can see the serial number. The serial number is usually written in a 4-digit year, a 2-digit month, 2-digit day, and then a serial number. So every time you make an edit to the information, you'd want the date written there, and then you start with 00, 01, 02, 03. You just count up. This would only allow up to 100 edits that day. And the serial number is used when you do zone transfers in order to figure out if the zone is already, well, if it's new or if it's the same zone. So if the serial number is the same, it will assume there are no changes and will not download the zone. So when you have your secondary servers out there, they need to make sure that the root server has serial numbers changing. The other numbers are refresh, retry, expire, default, time to live, those kinds of things. And those are all written in a number of seconds. So you can kind of get an idea of how long each one of these is. Some of the different types of records include your A records, your quad A or AAAA. You have your MX records, you have your CNAME records, your TXT records. There's all kinds of records. So you can see a couple of different examples here. The A records are for taking a name and converting it to an IP version 4 address. Your quad A records take a name and convert it to an IPv6 address. Your MX record is a record that takes a name and converts it into a priority and a name. And that is for your mail exchange. So if this were for the domain.ext or example.com, if you wanted to send an email to that domain, you need to figure out where your mail server is. And so that MX record right there indicates that you would go to the mail in the domain server. So maybe mail.domain.ext, and you can see the record right above it is an A record that tells you the IP address of that. Then you have a couple of CNAME records. CNAMEs are aliases, and CNAME stands for canonical name. So you can see that POP and IMAP both map to mail, and you can see mail maps to an IP address. And then you can see under the mail, in addition to having an A record, mail also has a TXT record, and the TXT record has what is called an SPF, and this is used to indicate which machines are allowed to send mail for that domain. So if you received mail for something, and this would probably actually be in the app, but if you receive mail for a given domain, you'd want to know who is authorized to send mail. So you can do a lookup using the SPF information in a TXT record and figure out which IP addresses are allowed to send mail. And this indicates that the entire 10. Network is allowed to send mail, but nothing else. So all other ones are not allowed. You also have reverse zones. So the top part of the reverse zone looks the same. You can see it jumps down to this origin thing. So origin to specify individual pieces. This is doing the 192.168.0 range. And you can see the 192.168.0.0 is that second to the bottom line, where it is in 0 in PTR for pointer, network.domain.ext dot. So it's telling you what the name of that, well, IP address is when you do a reverse lookup. And you can see the .1 as well. The named service needs to be started in order to start listening. You can use the systemctl command to start the named server. You just type in systemctl start named.service. You can leave the .service off if you want. Other options you have is the start, stop, restart, status. And then if you want to make sure it starts at boot time, you can use enable. And then if you want to remove that, you can use the disable to remove that so it won't start at boot time. In order to make DNS available, to really make it available, the DNS server needs to be able to receive data through the firewall. You need both UDP and TCP/53. 53 is only necessary if you're doing zone transfers, but normally DNS servers should be able to do zone transfers. So you want to indicate who can do zone transfers. So you can add the services or the service for the server with the command firewall-cmd space -- service equals DNS, and that will add in the service so that DNS can get through the firewall. If you want it to be permanent, you can do that same exact command with the -- permanent option, and then it will put it into the configuration file. So the next time the firewall starts up, it will add that rule in there. You can verify whether the services are present in the firewall currently with the firewall-cmd space -- list - all command, and that will indicate whether or not it is in the firewall. When you're troubleshooting, make sure the DNS server is set. And you can go look at the etcresolve.conf file, and you'll see which DNS server you have set, which is kind of important. You want to make sure you can talk to your DNS server in normal ways. You can use NSLookup, you can use ping, all kinds of things to make sure you can talk to it. Make sure the record is download okay. You can use NSLookup or dig. You can do a DNS hierarchy trace. So if you do a dig plus trace command on something, it will start from the root service and work its way down. You can figure out if you are in the DNS hierarchy. If you're not, then it's not likely anybody else will use you. You can make sure your firewall is correct. You can make sure logs look good. If you have any MX records or CNAME records, you want to make sure they point eventually to a valid A or quad A record. So CNAMEs can point to other CNAMEs and MXs can point to CNAMEs, or they can both point to A or quad A records. But eventually, if you keep resolving it, it should get to a quad A record. You want to verify the service is running. So you can use netstat, make sure it's running. And you want to make sure that any SE Linux contexts are not strange. So you can go look in the var named directory and see if anything looks like it doesn't have named in it. It might not work properly. And that is it for DNS. So good luck. Simple Network Management Protocol, or SNMP. The SNMP protocol is commonly used to gather statistical information from networking devices. It can grab all kinds of information such as bandwidth consumption, ports, whether they're on or off, names of machines. All this information can be gathered together and is usually used to manage an entire network. Some variables gathered can also be set using the SNMP protocol tools. SNMP typically operates on UDP ports 161 and 162. 161 for normal communication and 162 for traps or indications when there is a problem. There is a management information base, and well, this is for information. SNMP provides a lot of information. Each individual element of information can be addressed with a hierarchical dotted decimal number called an object identifier, or OID. The object identifier for system name or host name is 1.3.6.1.2.1.5, and this has multiple different pieces in it, and the very first one, which would be the system name, is .0. So if you have more than one name, it might be a .1 and .2, and it kind of increments up. To make things easier, the MIBs provide names for the numbers. You could get the same host name with that number above, or you can also use either system.sysname.0 or sysname.0. So those are a little bit simpler, easier to read and recognize and remember as well. Community strings. SNMP does not want to provide information to just anyone, so it requires a password called a community string. There are two default community strings. For read-only information collecting, you can use the default community string public. For read-write information collecting and setting, you can use the default community string private. SNMP uses the UDP protocol and the server ignores messages with the incorrect community string, so you do not know if datagrams were dropped or ignored. It's kind of confusing, makes it difficult. You send it out, you wait 10 seconds, nothing comes back, you say, well, it didn't work. But that could be because your community string is being ignored and there is no reply. Many network devices have active SNMP support the administrators are not aware of. It's very common for printers, for example, to have SNMP support turned on and running, and they might have both the public and the private community strings available. So you might be able to do all kinds of fun things with the printer, and the administrator wouldn't even know how you're getting in. Sometimes you have routers or wireless devices or cameras that all have SNMP support turned on and running. So you need to make sure you turn things off that should not have it running. Most SNMP messages are not secure. They send things in plain text, they come back in plain text. If you want to intercept something, you want to see what the community string is, just watch the line, see what it is. So some useful packages. NetSNMP provides the SNMP server. NetSNMP utils provides some utilities for performing queries and making changes. So you can do your SNMP get, SNMP set, your SNMP walk, all kinds of activities and utilities right there. When you're trying to configure the server, you need to go and edit the etc snmp snmpd.conf file. One of the most common changes people make is change the community string. You'd want to probably make it not be public. So you find the line that says com2sec not config user default public, and you can change the string to something else. For example, aloha123. which is also a super secure and secret password that no one will ever guess. The SNMPD service needs to be started in order to start listening. You need to use the systemctl command to start the SNMPD server. So just use systemctl start SNMPD, and you can use the .service if you want. Other options include stop, restart, status, enable, and disable. Enable is for making it start at boot time, and disable is to make it so it doesn't start at boot time. In addition to having the service running, you need to make sure it can get through the firewall. You can add the service to the firewall with the firewall-cmd --add-service equals SNMP. And if you want to make it permanent, make sure you add the -- permanent option to the end of that, and it will make it permanent. You can verify if the service is in the active firewall using the firewall-cmd --list-all command, and that will tell you which services are in the firewall. If you have it working, you might want to verify it's working. So you can use the SNMP client, which is provided, or the client utilities provided by NetSNMP utils, and I would recommend using the SNMP get and the SNMP walk commands to test your server. The following two lines assume your community string is aloha123, and you are just connecting to your local host, although you can put the IP address of the server you're connecting to if you have the firewall open. When you do the SNMP get and the SNMP walk commands, you want to make sure you pass the SNMP version. You can use 2C or 1, and you want to make sure you pass the community string with the -C option right there. In the top one, you are getting the system name or the host name, so it's sysname.0. And the SNMP walk, you're going to walk the entire system set of information. So sysname would be one of those items in the system set. And it'll just list a whole bunch of them, walk through it until it runs out of responding OID values. For troubleshooting, you want to make sure your DNS server is set correctly. Sometimes when you're trying to look things up by name, it can be a problem. You want to make sure you can talk to the SNMP server. You can ping it. You can port scan it. Make sure it's up. Make sure the firewall is correct. You can check your logs. You want to make sure the community string is correct. If you change it, you want to make sure you change your commands you're using to talk to it. You want to make sure you have the correct object name. And if you're having trouble talking to it, try something you know will work. So sysname.0. It's a good one to try. You also want to make sure the service is running, so you can use the netstat -tunap command to get a list of what services are there. And that is the end of this chapter.